Muy buenos días. Welcome to everybody. Good morning. We are very happy to have in this event. Well, first of all, I have to acknowledge to ICTP to organizing, helping all the logistics. Of course, to David and also Christian, Alejandro, and all the people that have been doing a big effort. All the staff of our institute, including all of our. In addition, I have to say that it's very important to have these events because for many people it's difficult to have access to top science, and for the students, mainly for the students in many of our countries, it's very difficult to travel to conferences or to take courses abroad. So this effort really helps us to have this opportunity. I hope that you enjoy the course, get all the benefits of it, and finally get the diploma, right? Well, that's all what I'm going to say. Welcome to Mexico. I hope to also to acknowledge to Institute of Geofísica that because our auditorium is in main reparation, right? So thank you very much and welcome to everybody. And I give you the microphone to Adrian Tompkins from ICTP.
Thank you very much. Welcome everybody. I'm from ICTP, the International Center for Theoretical Physics, which is based in Trieste in the northeast of Italy. If you don't know us, I know that I've a few faces I reckon. I know people have been, some people to some of our workshops. We're a Category 1 UNESCO Research Institute that's actually funded very generously by the Italian government, which has several different departments. There's mathematics, high energy physics, condensed matter. But from 1998, it also has a Earth system physics section, which has research on climate and climate change, oceanography, and so on inside the group. The Institute itself has a mandate to support global science. And as part of that, we support a range of workshops which can be hosted at our institute. So we have guest houses and so on workshops. So both Simona and Spencer, in fact, were contributing to a workshop we had last July on convection. That was a 3-week event with a conference embedded with a large group of people. So I know some people actually from UNAM have been either to that meeting or other meetings. And we also, so this meeting is part of this, should we say, category of our outreach in science support. I have to say very much a big thank you to Dave and you for hosting this as well for this week. It looks like it's going to be a fun and exciting week. What I need to say, one logistical thing is I've got badges here for everybody that registered through the ICTP website. So hopefully I have badges for most of you. So in the break, I will be distributing those. I know some of you are signing up already. And a free ICTP pen, woohoo! So no expense spared. So as you saw, I think basically the other thing I just wanted to quickly mention is, as well as the workshops, we also have a other range of activities that basically you might be interested in looking at. So we have exchange programs at all different levels. So for example, we have a sandwich program for STEP. It's called the STEP program for PhD students. So if you have, for example, a topic for a PhD that you think also fits with what we do, we have a program that basically funds students to spend in the order of 4 months per year. So you'd have a joint supervision. You'd have a supervisor in UNAM and a supervisor in ICTP, and you could actually have a joint research project with us. And that provides the opportunity to have 4 months each year at ICTP. And then we also have what's called the associate program, which is for more senior scientists. I actually, from basically postdoc. So it can be junior, postdoc, mid-career, and also senior. There is more emphasis in that program on the junior and mid-career, but it's possible right up to retirement to actually win that possibility. And that is also a program that basically allows you to come to ICTP 3 times in a 6-year period. It funds your journey and your accommodation and so on to be able to interact scientifically with people in the group. There are other programs. I don't want to go into details because we're a little bit behind on the schedule, but I invite you to have a look at the ICTP website to see if there are opportunities there, and also just have a look at some of the workshops and so on that you might find interesting to actually join, either in person, but we often have these things hybrid remotely. So join them if you so desire. Okay. I think that's all I wanted to say. So I'll kind of hand over the microphone. Say once again, thanks for coming along. So I think Dave wants to have a few other words about also logistics and how we're going to be arranged. So for the lectureships and
yeah. Okay, great, thanks. Yeah, it's very interesting. I remember when I was doing my PhD back when there were dinosaurs on the planet, and I remember reading the work of Adrian Tompkins and thinking about it. And then now I realize he's taller than me and knows karate, so I'm not going to debate things with him. Okay, so basically, we have a couple of logistical things. Most of these things you're probably already familiar with, but let me just clarify. There's been a kind of a little small change in the order of talks. I'm going to give another one on Wednesday in addition to the one today. And then Jorge exchanged with Simona on Wednesday also. Okay, now every time the people who are registered for the ICTP diploma or the Educación Continua, you have to sign in every day, like the thing that I just passed you, and make sure it gets back to us, me or Christian or Alejandro. There's going to be coffee breaks, and I guess we're going to do it right here outside of the auditorium, and they'll be for the 3 days at 11 a.m. here for the seminar series. Oh, I was also told don't bring coffee or food in here. Okay. Our lunch is at 1:30 or 13:30, and it's going to be across the alley there. What do we call it? The pathway in our institute, and then in the patio back. Okay, and that will be at 1:30. I think except for Thursday, I think there's a small change. It's at 1, Alejandro. 30 minutes. I think it might be a little bit earlier, but no big deal. We're going to do an event photo, and I understood we're going to do it over here somewhere, right outside here. Okay, and that will be on Wednesday at 11 a.m. The hands-on part, again for the Educación Continua, the diploma people, that's in the Sala Audiovisual, which again is across the way in our institute. One thing that's important, save your questions for the ends of the talk, just to avoid the chaos. And what we need is for you to use the microphone too, because of people online listening to the program. I think that's it, but I definitely want to thank the local committee here, so particularly Alejandro, Christian, and Arturo. Also was big help from Yoali, Barbara, Marbella, y Giselle, and I'm sure others that I'm forgetting. And then also Vanessa and the people associated working with her. So I guess we can start now with Simona Bordoni. Okay, so come on. Right now? Oh, okay. She wants a picture right now. Everybody. Sorry. I got my microphone. Do you want me to sing a song? Ni lo reconocí. Ya se ve más betabel.
Las preguntas. Apágalo. El botón.
Okay, good morning, everybody. While the projector starts, I just wanted to say that I'm going to give a very basic introduction to thermodynamics and stability. I hope that this is something that you guys have seen before, but it's to make sure that we're all on the same page, and then we can build up with more advanced material, starting from this more basic introductory lecture. You'll see that I'll do things a little bit differently. I will annotate my slides so that if you guys want to take notes, you can do it following what I annotate on my iPad. Hopefully this will work. Usually I give this lecture sitting down. I should also warn you that my handwriting is not the best one, so bear with me. Okay, so we are going to start with a very quick review of dry thermodynamics. So how do we write the equation of state for dry air? This is just the ideal gas law, where we have this relationship between pressure, density, and temperature. Should I hear an echo? Oh, I know what I need to do. Sorry. There should be a way for me to disconnect my... No, I should disconnect. Let's see if I can do this. Okay, I think hopefully this will work better. Okay, so again, the ideal gas law is just a statement that pressure is equal to the product of density, the gas constant for dry air, and temperature, where the gas constant for dry air is just equal to the universal gas constant divided by the molecular weight of dry air, with the molecular weight of dry air being about equal to 28.97 grams per mole. And this gives us a gas constant that is equal to 287 joules per Kelvin per kilogram. So how do we write the first law of thermodynamics? I'm going to write this for an infinitesimal transformation. And the first law of thermodynamics is just the statement that any change in the internal energy, that for an ideal gas, we can just write as the product of the specific heat at constant volume multiplied by the change in temperature for the infinitesimal transformation that we are considering, plus the work done, that for an ideal gas is equal to the pressure multiplied by the change in specific volume, and this will have to be equal to any heat that is being exchanged between the thermodynamic system and the environment. And here the specific volume V is just equal to the inverse of density. If we now integrate the first law of thermodynamics over a cyclic transformation being one in which we start from one state, we go through an intermediate sequence of states and we go back to the initial state, and this is the symbol that we use. This is denoting, again, an integral over a cyclic transformation. Again, I'm going to rewrite the first law of thermodynamics, just integrating over this cyclic transformation. And so notice how temperature is a state variable, and so the integral over a state variable will go to 0. And this term here is just the total work that the system done in this cycling transformation, and this will have to be equal to the heat that the system absorbs over a cyclic transformation. And that is why the first law of thermodynamics, we state it in many different ways. It's it's a conservation of energy statement. Is also a statement that work is equivalent to heat in the sense that a system cannot put out as work in a cyclic transformation more energy than it absorbs as heat during this transformation. However, when we write the first law of thermodynamics for instance, any air parcel, we do not like to use temperature and volume as our state variables for many reasons, including the fact that we often use pressure as our vertical coordinates. We'd rather use pressure as our state variable. And so we manipulate the first law of thermodynamics so to use pressure rather than volume as a state variable. And so I'm going to do something very simple. Again, I'm going to rewrite the change in internal energy over this infinitesimal transformation. But then I'm going to rewrite this term, P dV, using the chain rule. And so I can rewrite this as the differential of the product of pressure and specific volume minus, of course, volume multiplied by the change in pressure. I'm going to use the fact that the specific volume is equal to the inverse of density. So I'm going to get this term. And again, this still needs to be equal to the change, the exchange of heat in this transformation. Of course, I hope that everybody can see that the product of pressure and volume is just equal to the gas constant for dry air multiplied by temperature. And so these two terms can be combined in one. And so I get that CV plus the gas constant for dry air multiplied by the change in temperature in this infinitesimal transformation minus 1 over rho change in pressure is equal to the heat exchange during this transformation. And so for dry air, which is basically can be considered as a diatomic gas because it's made primarily of diatomic molecules, the specific heat at constant volume is equal to 5/2 multiplied by the gas constant of dry air, which is equal to 717 joules per Kelvin per kilogram. The sum of the the specific heat at constant volume and the gas constant of dry air is nothing else but the specific heat at constant pressure. And the specific heat at constant pressure, therefore, is equal to 7/2 multiplied by the gas constant of dry air. And this is a very easy number to remember. It's about 1,000. To be more specific, it's 1,005 joules per Kelvin per kilogram. And so finally, we get to the way in which we usually write the first law of thermodynamics for dry air. It's just a statement that the specific heat at constant pressure multiplied by the change in temperature, again in infinitesimal transformation, minus 1 over rho multiplied by the corresponding change in pressure will have to be equal to the heat that the system is exchanging in this transformation. I want now to introduce some important conserved variables. And again, right now we're working with dry air. Of course, we will have to introduce moisture at one point, and I want to define these conserved quantities that I think you guys have seen in dry thermodynamics, because then we'll generalize them to account for the presence of water vapor and the possibility that water changes phase, because this is really one fundamental way in which water vapor influences the dynamics, thermodynamics, and even radiative properties of our climate system. Okay, so the first quantity that I want to introduce is enthalpy, which is conserved under an adiabatic and isobaric process. Isobaric means that there is no change in pressure in this transformation. Think about of an air parcel that is moving in the horizontal direction. So its pressure does not change. And it's also adiabatic, means that there is no heat that is being exchanged in this transformation. So again, we don't have any change in pressure. dP is equal to 0. We don't have any change in any heat exchange. dQ is equal to 0. And therefore, we can introduce a quantity that is called enthalpy that is conserved under this transformation. In particular, the definition of enthalpy, which I am going to denote with the letter H. I always make this joke. I teach thermodynamics to my students every year. There's more variables in atmospheric thermodynamics than there are letters of the alphabet. And in fact, unfortunately, there is a lot of confusion. The same letter is used to denote different things. So always make sure that you know what we are actually looking at. And so, again, so enthalpy here I'll denote by H, dry enthalpy. It is the sum of the internal energy U plus the product of pressure and the specific volume, where again, for an ideal gas, the internal energy is just, we already used this definition to write the first law of thermodynamics, is the product of the specific heat at constant volume and temperature. And if we introduce this, again, I hope that you guys can see, I won't redo the derivation, but we can write the first law of thermodynamics just introducing the change in enthalpy dH minus 1 over rho dP. And again, this will have to be equal to the heat that is being exchanged in this transformation. So now we really introduced in our first law of thermodynamics, we basically introduce directly this variable enthalpy. And so again, to go back to the conservation property of this variable, if now we assume an isobaric transformation, again, no change in pressure, dP, the differential of pressure, equal to 0, and no exchange of heat, dQ equal to 0, it follows, therefore, that there cannot be any change in enthalpy. For such a transformation, the differential of enthalpy will have to be equal to 0. That is to say, enthalpy will have to be conserved. And enthalpy is similar. And let me also rewrite here how enthalpy H, again, this is something that becomes obvious. If we now rewrite, we compare the first law of thermodynamics written in terms of enthalpy with this form of the first law of thermodynamics. Enthalpy is just equal to the specific heat now at constant pressure multiplied by temperature. And enthalpy is similar to internal energy, but also accounts, not only, it doesn't only takes into account the internal energy, but also it accounts for the work that the thermodynamic system, and in our case, our thermodynamic system is an atmospheric air parcel, can do in its environment. Okay, so for instance, again, here I don't have time to go into examples of how we use this conserved quantity, but for instance, think about air masses, for instance, of different temperatures that mix when they move horizontally. Okay, but let me here introduce, before I move on, hydrostatic balance. We'll use this several times during this lecture. What is hydrostatic balance telling us? It is just a statement that in the vertical direction, there is a perfect equilibrium between the gravity force and the vertical pressure gradient force, so that an air parcel, in fact, here we assume that it doesn't move. In reality, hydrostatic balance would say that it doesn't have any net acceleration. So again, here, this will represent my vertical coordinate z. And so if we now consider an air parcel, this is my air parcel, hydrostatic balance is just a statement that any downward pull due to gravity acting on this parcel will have to be balanced by the upward pull due to the pressure gradient force. And I'm going to just write this again. This is the vertical component of the pressure gradient force. And because the pressure gradient force acts from high to low, this is already telling us that the pressure gradient force to point upward, so to balance the gravity downward pull, pressure needs to decrease as we go upward in height. Okay, so this is again just something that we can say even without being any more quantitative. But if we can be more quantitative, we can write explicitly what hydrostatic balance is. Again, the pressure gradient force, and here I'm just assuming now that pressure does not depend on the horizontal direction, so I can just write the pressure gradient force as one rho, the inverse of density, multiplied by the ordinary derivative of pressure with respect to height, minus g. And for the hydrostatic balance to hold, this will be need to be equal to 0. Again, the statement is there is no net acceleration. If now you use the equation of state for dry air, I'm not gonna rewrite this, we can rewrite the hydrostatic balance expression introducing a scale height such that dp over p will have to be equal to minus dz divided by h. And in this case, I haven't made any assumption of how temperature might depend on height. The scale height is a function of height, and in particular, the scale height will be equal to the product of the gas constant of dry air multiplied by temperature, that again, so far, I'm assuming might be depending on height divided by g. And again, I let you to convince yourself that this is in fact is a height in the of length. We can now make the assumption of an isothermal atmosphere. And of course, we all know that our atmosphere is not isothermal. But one big difference between pressure and, for instance, temperature is the fact that pressure, and we will see, in fact, how, I'll have a plot to convince you that this is the case, decreases exponentially with height. So through the depth of our atmosphere, pressure changes through many, many orders of magnitude, whereas temperature remains more bounded. And so even if our atmosphere, we all know it's not isothermal, some very simple scaling arguments can be derived, assuming that indeed our atmosphere is isothermal. And so I'm going to write here that for an isothermal atmosphere, isothermal meaning that temperature is constant. Again, here I'm going to assume that T, in fact, is independent of height and is just equal to a constant temperature. And here I'll just take a mean atmospheric temperature value of about 260 Kelvin. Again, here we're not trying to really be very specific. We're trying to make orders of magnitude calculation. I'll let you show that, again, this is a very easy calculation. The scale height, of course, will also be a constant, and it's about 7 kilometers. And so now we can integrate this very simply. It's just, of course, will give us an exponential decaying behavior for pressure, and in particular, pressure as a function of height will be equal to the surface pressure multiplied by the exponential of minus z divided by this constant scale height h naught. Okay? And again, typical surface pressure values is about 1,000 millibar or 1,000 hectopascal, 10 to the 5 Pascal. And so this is exactly to show us the pressure changes as a function of height. And we see that, in fact, this is very much an exponential behavior. Here to introduce conserved quantities that are conserved under assumptions that will become progressively less restrictive. We all know that the basic of atmospheric convection is air parcels going up. So, of course, enthalpy is useful only if you consider horizontal motions of air masses. But, of course, it doesn't allow us to think about convection, which is one of the things we are most interested about. And so, of course, we want to relax the assumption of constant pressure. And so the first assumption, the first step that we can take is assuming that, again, pressure is not constant anymore, but it changes hydrostatically, okay? And so let me go back to the first law of thermodynamics. I'm going to rewrite it in terms of enthalpy. So we wrote that dH minus 1 over rho dP will be equal to the heat that is being exchanged in this transformation. If now we make the assumption that pressure changes hydrostatically, and let me make this text a bit bigger so that everybody can see that. If now pressure changes hydrostatically, we can use the fact that minus 1 over rho dP will have to be equal to G dZ. And this is nice because now we are getting rid of the density, which of course is a function of pressure and temperature. And so we can rewrite now the first law of thermodynamics such that the differential of the sum of enthalpy plus Gz, which is nothing else but basically a potential energy, will have to be equal to the heat exchanged in this transformation. So I can introduce another variable, which is called dry static energy, which I will denote with the letter S, which is the sum of dry enthalpy plus Gz. And now I hope that everybody can see that if dq is equal to 0, so now if we make the assumption of an adiabatic transformation, now it's dry static energy that is conserved. That is, ds will have to be equal to 0. Okay? But still, especially when we think about convection, the assumption, oh, and here maybe let me make this point, because of course I didn't quite say it. I wrote down hydrostatic balance. In reality, really, the equation that I wrote down is really one of hydrostatic equilibrium, where I assumed a completely atmosphere at rest. It turns out that at least for large-scale motions in our atmosphere, we can still assume hydrostatic balance to be a good approximation to the vertical momentum equation. And what this means is that in reality, the parcel is not at rest. It might even have a vertical acceleration, but that acceleration term is much smaller than the other terms that appear in the vertical momentum equation, so that at the leading order, we still have a balance between the vertical pressure gradient force and the gravity force. And one can show that this is verified for motions that are large scale, that is, for motions whose aspect ratio, that is the ratio between their vertical extent and their horizontal extent, is much smaller than 1. Of course, this does not apply, for instance, to convective motions, and so one might want to introduce a quantity that is conserved just under the assumption of an adiabatic process. And again, here I've been a little bit sloppy at defining adiabatic. When we really talk about adiabatic in thermodynamic equilibrium, here what we are assuming is that the process not only is such that there is no heat that is being exchanged with the environment, but also such that it's a reversible process. And so for a reversible process, it turns out that we can introduce another state variable that is called entropy. And here I can only define it. I don't really have time to go into the many intriguing aspects associated with this quantity. But entropy, again, for a reversible process, there exists another state variable, entropy, such that in a transformation, the change in entropy, and I'm going to denote entropy with this Greek letter eta, is equal to the ratio between the heat exchanged in a given transformation divided by the temperature at which this transformation is occurring, or the temperature of the heat source from which with which the system is exchanging heat. And again, I'm going to go a little bit quickly here, but if we go back to this form of the first law of thermodynamics, if now we divide by temperature, we can rewrite the first law of thermodynamics all in terms of state variables. Because again, let me emphasize this. Heat is not a state variable. Work is not a state variable. We cannot talk about the heat or work of a given state. We can only talk about work and heat that are being exchanged in a given transformation. So now, if we divide by temperature, the first law of thermodynamics, we can rewrite it all in terms of state variables. In particular, we get that Cp multiplied by dt over T minus 1 over rho T multiplied by dP, and this will be equal to dq over T, which, as we know, is equal to d eta. Again, I want to rewrite this in a little bit nicer form, so I'm going to be using the ideal gas law, so I can rewrite the first law of thermodynamics as Cp dt over T minus R dry dP over P, and this will have to be equal to the change in entropy in this transformation. And notice how this is interesting, because now these are just the differential, the logarithm of temperature and pressure. And so for an isentropic transformation, which is an adiabatic and reversible transformation, and so let me write this here because this is an important assumption. So for an isentropic transformation, one in which entropy remains constant, d eta will be equal to 0. And so we can rewrite the first law of thermodynamics such that Cp multiplied by the differential of the logarithm of temperature minus R dry multiplied by the differential of the logarithm of pressure will have to be equal to 0. I'm going to use the properties of logarithm so that I can rewrite this, again, these are just a few very easy steps, as the differential of the logarithm of temperature, the product of temperature and pressure to the minus R dry over Cp. And this whole thing will have to be equal to 0 in an isentropic transformation. And what this means is that for an isentropic transformation, the product of temperature and pressure to the minus R dry over Cp will have to be equal to a constant, will have to remain constant. Okay? Any questions so far, by the way? Okay, good. So this is really the basis to derive a temperature variable that we call the potential temperature. That is the temperature that a parcel with a given temperature and a given pressure would have if we brought it adiabatically and reversibly to a reference pressure P naught. Therefore, under this assumption, again, we start from a given parcel, given temperature and pressure. We bring it to a reference pressure P naught. We're going to call theta, potential temperature, the temperature that the parcel acquires at this reference pressure P naught. Therefore, given that this needs to be true, we can define the potential temperature such that T, the initial temperature of the air parcel, multiplied by its pressure to the minus R dry over Cp, will have to be equal to the potential temperature theta that the parcel gets at this reference pressure P naught to the minus R dry over Cp. And therefore now we can we can invert this relationship to obtain an expression for potential temperature theta, which is equal to the temperature multiplied by P naught divided by P to the R dry over Cp. And by convention, P naught, this reference pressure P, is taken as 1000 millibar. Okay? And so, of course, by its own definition, potential temperature is conserved in an adiabatic transformation. And one can show, I'm not going to do it, that in fact potential temperature is our proxy for entropy. But we don't like, atmospheric scientists don't like to think about entropy. We like to think about temperature. In fact, whenever possible, we introduce temperature variables because, of course, temperature is, for instance, what drives buoyancy, as we will see and temperature is a quantity that, of course, we're very familiar with. And again, one can show that there is this tight relationship between entropy and potential temperature, and in particular, entropy eta of an air parcel is equal to the product between the specific heat at constant pressure and the logarithm of potential temperature plus undefined constant. Okay? Okay, so the one thing that maybe I would like to say about the use of this conserved quantities, again, I don't have time to go into showing you how powerful these conserved quantities are, but many times we like to think about following the evolution of an air parcel, for instance, when we think about Lagrangian approaches. And we always give as an example, let's suppose that we can paint a parcel red or a parcel blue, a parcel green, and we follow as they move around, assuming that they retain their identity. We cannot do that in practice, but we can tag these different air masses, different air parcel, based on the corresponding values of a conserved quantity. And so potential temperature, again, under the assumption that we can assume that potential temperature is conserved, we can tag these air parcels as blue if, for instance, is characterized by a low potential temperature. Red will be a parcel that will be characterized by a warmer potential temperature, and so on. And we will see that potential temperature will really feature importantly when we think about stability of a dry atmosphere. Okay? Okay, so now I want to use the first law of thermodynamics to derive a very, very important quantity, which is the dry adiabatic lapse rate. And this represents the rate at which temperature decreases if we move an air parcel up, or increases as we move an air parcel down. And then I'll derive the expression, I'll just then comment very quickly about the physical meaning of this very fundamental dry adiabatic lapse rate. So let's assume that, again, we are considering a transformation that is adiabatic and in which pressure changes hydrostatically. And so in this case, this quantity, dry static energy, is conserved. And so again, let me write it here. So again, for this transformation, again, here we're assuming that its pressure changes hydrostatically. It's an adiabatic process. The dry static energy will have to be conserved. Dry static energy comprises two parts, dry enthalpy and potential energy. This means that in an air parcel, there can be, as it goes up adiabatically, there can be exchanges between these two forms of energy, but in such a way that dry static energy does not change. So we get that, again, the product of the specific heat at constant pressure multiplied by the change in temperature as the parcel goes up, plus Gz multiplied by dz, that is the change in height, will have to be equal to 0. So we can now invert this relationship to obtain an expression for the rate at which temperature changes in this adiabatic process. And so I'm going to write it here. So again, the change in temperature with height in a process that is adiabatic. Therefore, both entropy and potential temperature are kept constant. This is what this notation denotes. Will have to be equal. Again, just inverting this form of the first law of thermodynamics will be equal to minus G divided by Cp. So in reality, because we all know that temperature on average, unless we have inversions, decrease with height, lapse rates are defined changing signs so that they are positive. They're just the rate at which temperature decreases. So we can define the dry adiabatic lapse rate, which is denoted by the capital Greek letter gamma with, again, the subscript d, will be just equal to minus the lapse rate that we have just derived, the change of temperature with height in this process in which theta and eta remain constant, and this is just equal to G over Cp. And this is the very familiar rate of about 10 Kelvin per kilometer. Okay? Again, just physically, what does this mean? If we take an air parcel under the assumption that, again, it's still a dry air parcel, and it goes up adiabatically, it will undergo an expansion because it finds itself at a lower pressure. This expansion needs to occur at the expenses of the internal energy, which is a function of temperature, and that is why temperature decreases. But really the important aspect, we will see this is not the case. It does not carry over when we consider the presence of moisture in an air parcel. The nice thing about the dry adiabatic lapse rate is that this is just the constant. It's completely independent of height. If you take an air parcel from the, let's say, somewhere in the middle atmosphere, and you lift it up or you lift it down, or if you take it from the surface, the decrease, the rate at which temperature decreases if you take it up or increases as you bring it down is always the same, completely independent of height. Okay, so then let's move on and talk about stability. Here you will see that I won't be able to do all of the derivations. I only have about 2 hours to talk about a lot of things. So I'll skip a few steps. But here now the question is, what is going to happen if we take an air parcel that is at the beginning at equilibrium with its background environment, which is very happy to be in a state of pure hydrostatic equilibrium? What happens if we lift it up? Of course, its fate will depend as to whether it will find itself warmer than the background environment at the height to which we displaced it, or it will find itself colder, or it will just have the same temperature. In the former case, it will be more buoyant. It will be further accelerated upward. If it's colder, it will it will be denser, so it will feel a downward pull that will bring it back to its original height. And if it's just at the same temperature or density of the background environment, it'll just be happy to stay there. So again, here I'm just going to very schematically denote as to what we're thinking of. This is as before my air parcel that we assume starts from a given height, z equal to z naught. Usually we take that as the surface, but these arguments apply to any height for that matter. Again, at the beginning, we're just assuming that this parcel is in perfect hydrostatic balance as the background atmosphere. That is to say, we have this balance between the pressure gradient force and the gravity force. And we are going to ask ourselves what's going to happen if we lift the air parcel up by a small vertical displacement delta Z. Okay? So this is our starting point. And so we're going to use the parcel method. And what is this parcel method? This parcel method is based on a number of assumptions. So we are going to assume that as we lift the parcel up, it moves adiabatically, doesn't exchange any heat with the environment. It also doesn't mix with the environment. The pressure of the parcel adjusts instantaneously to the ambient pressure. We'll see that this is just equivalent to stating that density differences between the parcel density and the background environmental density are all driven by temperature differences. The parcel does not disturb the environment. We know that this is another big assumption. And we also are going to assume that the environment is in hydrostatic balance. So in the following, I'm going to denote with the subscript E all of the variables that pertain to the environment. So temperature, pressure, density. And I'm going to denote with the subscript P the corresponding values of this, the same quantities for the parcel. So again, this is for the environment. And this is for the parcel. Okay, so so we're going to try to use all of these conditions to, again, find ways in which we can discriminate what's going to happen when we lift an air parcel up. So condition 4 is a condition of hydrostatic balance for the background environment. So again, let me write this here. Condition 4 implies, and this is a statement that is valid for any height, but here let's assume that this is the, again, rewrite it for height z equal to z naught from where the parcel is being lifted up. And so again, condition 4 implies that we have this perfect balance between gravity and the pressure gradient force. And again, here I'm writing ordinary derivatives because I'm assuming, for instance, that there is no dependence on x and y. Again, here now, this is valid for z equal to z naught, from which we are lifting our parcel by an amount delta z. Okay? Okay, so now we put the air parcel here at delta z. And before, it was like the background environment. It was part of completely in hydrostatic balance. When we lift it up, there is no guarantee that the parcel will still be in hydrostatic balance. It might have a net vertical acceleration arising from a disimbalance between the gravity pull and the pressure gradient force acting on it. And so we will have to therefore now write down, and again, I'm writing the momentum, the vertical component of the momentum equation of the air parcel at height delta z. So again, it might feel a vertical acceleration. W here is just the vertical velocity. So this is the time derivative of the vertical velocity, vertical acceleration. And this will be equal to minus g minus, and I'm going to just write the pressure gradient force, but I'm going to write it in a way that we are reminded here we are looking at the vertical momentum equation at height z naught plus delta z, because we have displaced the parcel up. So the density here that appears, the inverse of density, is computed at z naught plus delta z, and the same will be true for the pressure of the parcel, whose gradient with height determines the pressure gradient force at height z naught plus delta z. One of our assumptions, in particular, assumption number 2, states that the pressure of the parcel adjusts instantaneously to the ambient pressure. So here, what this statement is equivalent to say that the pressure that the parcel feels at height z naught plus delta z will just be equal to the pressure of the environment at the same height z naught plus delta z. And so we can replace it in here. I'm going to skip a few steps here. We're going to use the fact that hydrostatic balance holds for the environment, at each height. And so therefore, with some manipulations, we can, again, using basically these conditions, we can rewrite that the vertical acceleration of the air parcel at height z naught plus delta z will be equal to minus g plus g that multiplies the ratio between the density of the environment at that of the parcel at height z naught plus delta z. And so therefore, this is just equal to g multiplied by the fractional density difference between the environment and the air parcel. That is the density of the environment minus the density of the parcel normalized by the density of the parcel. This whole thing here is what we call the buoyancy force. And what is its sign? That's what I'm going to write here. So the sign of the buoyancy force, as I said before when I was trying to describe in very simple terms what's going to happen to an air parcel when we lift it up, depending on the magnitude of its pressure relative to the background pressure. If the density of the parcel at height z naught plus delta z is larger than the density of the background environment, the parcel will be denser than the background environment, so it will feel a downward pull. The buoyancy force will pull it down, so the buoyancy force will be smaller than 0, and the parcel, again, will be, the buoyancy force is trying to pull the parcel back to where the height from where it started from. If the density of the parcel at this height is equal to that of the background environment, there is no net buoyancy force. And if the pressure of the parcel is smaller than that of the environment, the parcel will be lighter, less dense, and so the buoyancy force will be positive, and so the parcel will feel a force that will pull it even further away from the height from which we displaced it. Okay, and so the three conditions correspond to a stable condition. The first one, the parcel will want to go back to where it started from. This second condition is a condition of neutrality. Nothing happens. The parcel doesn't feel any net force if we displace it. And then the third condition is a condition of instability. This is an unstable condition because the parcel will feel a force that will pull it further and further away from where it started from. Okay? And so to make an analogy to mechanical systems that you might be familiar with, the condition of neutrality is similar to the condition of no change in any potential, that again, any object might be moving along. So this would be corresponding to a situation where, again, we displace any body along a uniform potential field. So this will be our neutral situation. Stability would be corresponding to a situation where any object or body would be at the bottom of a potential dip, of a potential minimum, so that if you displace it in any direction, it will oscillate back and forth around this stable equilibrium. This will be our stability situation. Let me use the same color. Whereas in case of instability, of course, you would be sitting here at the top of a maximum in your potential field, so that again, if any displacement will accelerate our body further away from this unstable equilibrium. So this would be our situation of instability. Okay, so this is great. We have an expression for the buoyancy force. We even can understand its sign. But now we want to be a little bit more specific. We want to derive conditions on temperature and density profiles that will allow us to discriminate as to whether we are in a stable or unstable situation. And so again, I am going to go very quickly through this. I don't have time to go through all of the intermediate steps, but this is very simple. We're going to be doing a first order Taylor expansion of density, both for the environmental density and the parcel density around Z. Sorry, here we are, I just wrote down Z equal to 0, but to be more general, this would be any Z naught from which any height from which the parcel is displaced. We're going to express density in terms of both temperature and pressure, but because pressure does not come into play, because we assume that the parcel pressure adjusts instantaneously to the parcel pressure, basically, it's really changes in temperature that really here are running the show. And so again, the vertical momentum equation becomes, if you do all of this manipulations, and again here I'm going to be writing it also using the fact that, of course, the vertical acceleration is the first derivative of the vertical velocity, but it's the second derivative of the vertical displacement, delta Z. We can rewrite the vertical momentum equation in this compact way. This linear operator given by the sum of the second time derivative plus n squared, and I'll tell you in a minute what this n squared is, applied to the vertical displacement will have to be equal to 0, where the square root of this n, here, what appears here is the square of this parameter n is the Brun-Weisela frequency. So as the units of inverse of time. And so now the solution of this very simple, I hope that everybody recognizes that this is nothing else but a linear harmonic oscillator. The solution to this very simple differential equation is such that the vertical displacement as a function of time will be equal to the sum of two exponential function of time, particular a multiplied by the exponential of I and t plus another constant multiplied by the exponential of minus I and t. And if n squared is positive, these are oscillatory solutions, sines and cosines. Such that the period of oscillation of the stable solution is related to the inverse of the Brun-Weisseler frequency. So really, this is a frequency. Whereas if n squared is negative, this will be, we have exponentially one solution that will be exponentially damped, but then we have another solution that will be exponentially growing. So this is an exponentially growing solution. Growing solution. So again, the first case represents our stable situation, and our second case corresponds to our unstable situation. I didn't want to do that. Unstable situation. And if n squared is equal to 0, we are in our neutral case. And so now we were able, and I haven't given you a definition of the Brun-Weisseler frequency, but I'm going to do this in a second. We now were able to trace back, to be able to derive conditions for stability or instability to a vertical displacement in terms of the sign of the square of the Brun-Weisseler frequency. And again, by following the steps that I have listed on this slide, you can show that the square of the Brun-Weisseler frequency is equal to G divided by T naught, the temperature at the height Z naught, multiplied by the difference between the lapse rate of the environment and that of the air parcel. And here, we're going to assume the other very important first assumption that we made when we derived this, when we use the parcel method, that is, the parcel behaves adiabatically. If it behaves adiabatically, then the rate at which temperature decreases when we displace the parcel up is the dry adiabatic lapse rate. Okay? And so again, inverting the sign, because as I said, lapse rates are defined as positive numbers, just the rate at which temperature decreases. We can rewrite the square root of the Brun-Weisseler frequency as G divided by T naught that multiplies the difference between the dry adiabatic lapse rate minus the environmental lapse rate. Let me here emphasize how the parcel in our assumption always moves adiabatically. So we know exactly what the lapse rate of the air parcel is, the rate at which its temperature decreases. So really here, the factor that discriminates between a static stability or instability case is the environmental lapse rate, which is what we go out and measure with radiosondes and is determined by many processes, including convection, advection, radiation. Okay, so that is discriminating factor. What is the magnitude of the environmental lapse rate relative to that of the dry adiabatic lapse rate? And one can show, and this is where potential temperature comes back in, that we can also express the square of the Brun-Weisseler frequency in terms of the vertical profile of the environmental potential temperature. And in particular, one can show that the square root of the Brun-Weisseler frequency is proportional to the vertical gradient of the environmental potential energy. And again, here, let me quickly rewrite, just to be, but again, n squared positive means stability, n squared equal to 0 means neutrality, n squared negative means instability. Okay, so I'm gonna do this super quickly because then I wanna move on to moist thermodynamics. Let's try to graphically understand, again, what the implications are in terms of the environmental lapse rate to determine stability or instability. Okay, so this will be, and again, here, I won't go into the details of what are the thermodynamic diagrams that we use. Let's just do a very simple diagram. We're gonna put temperature as our, and this is a little bit one another confusing aspect of thermodynamic diagrams. We put basically our independent variable z on the y-axis, and we put our dependent variable, in this case temperature, on the x-axis. But that, of course, once you get used to it, it's just a very simple way to visualize as things change in the vertical direction. And so again, here, what really demarcates stability from instability is the dry adiabatic lapse rate. The dry adiabatic lapse rate is fixed. We exactly know what it is. And so here, I'm gonna draw the profile, the decrease of temperature following the dry adiabatic lapse rate. And as we know, that is going to be just a straight line. This is it. This is my dry adiabatic lapse rate. Okay, so I'm gonna denote this as gamma dry, and what I mean by that is that if I take an air parcel from the surface, or for that matter from any height, we exactly know that the temperature of the air parcel will need to be following this line, okay? So if the parcel starts from here, we lift it up, we lift it down, it will go up and down, its temperature will go up and down along this fundamental line, as we call it, okay? Then the question, how can we know if, again, under certain environmental conditions, if through any way, and I think that maybe Adrian later on will talk a little bit more about what are these mechanisms by which we can lift air parcels up, maybe. Right now, we're just doing these thought experiments. Then again, we want to discriminate whether what's going to happen. Will the parcel be able to freely convect and be accelerated further upward, or will waves that are gravity waves be generated in the atmosphere under stable condition? We go out and measure the environmental temperature profile, okay? And so here, pardon me, this very simple simplification, I'm going to draw the environmental temperature lapse rate as a straight line. It's not a straight line, but right now we're just thinking about infinitesimal changes. So you can imagine taking the tangent to that from the point from which we start. And so now I'm gonna draw a case in which the environmental lapse rate is smaller than the dry adiabatic lapse rate. What this means is that the temperature of the environment decreases less rapidly with height than the dry adiabatic lapse rate. And again, if I now draw this as a straight line, again, we know that is not the case. This is where the environmental lapse rate would be. Here, this would be my TE. And this is a condition of stability. And I'm going to do this just for the stable case. You guys repeat to yourself for the neutral and unstable case. But what does this mean? Why is this a stable situation? If I take an air parcel up, again, remember, we need to compare temperatures at the height to which the parcel is displaced. And so if I lift an air parcel up, it always follows the blue curve. So it goes up here. And then, is it colder or warmer than the environment? We now compare, and we see that it's colder than the environment. So it will sink back because it's denser, okay? And so all of in this parameter space, you can think of this as a parameter space, for all of the lapse rates, environmental lapse rates, smaller than that are on this diagram to the right of the dry adiabatic lapse rate, all of this, again, you can imagine an infinite number of lapse rates that are to the right of this fundamental line. This defines my condition of stability. Instead, for lapse rates that are larger than the dry adiabatic lapse rates, which means in which temperature of the environment decreases faster than the dry adiabatic lapse rate. So now I'm on the left on this phase diagram, parameter space, whatever you want to call it. Again, all of this lapse rates, environmental lapse rates, will correspond to a situation of here, instability. Okay, I hope this is clear for everybody. Are there any questions? And again, this is really forms the basis of what we're going to be looking at when we introduce moisture. Okay, let me also here emphasize how we can rewrite this, the square and this stability conditions in terms of the vertical profile of the potential temperature. Again, n squared positive, which means potential temperature increasing with height, stable. N squared negative, that is potential temperature decreasing with height, unstable. So if we look at the observed distribution of the potential temperature, and this is for the annual mean and for the zonal average. So what we've done here, we just, as every single latitude, we average in longitude, and then we look at how potential temperature decreases with height on a meridional plane. Again, height is here and latitude is here. This is a bit blurry, sorry. This is the equator, North Pole, South Pole. Increasing shades of green indicate larger values of potential temperature. It turns out that everywhere, almost everywhere in the free troposphere, there are some places in the boundary layer, for instance, over dry desert regions, where this is not the case, but almost everywhere, especially on the large scale, potential temperature is increasing with height. Our atmosphere is stable in a dry sense. And yet we know that convection happens all the time. If we were to look out right now, go out, we will see clouds, which of course are a signature of convection. So why? What did we do wrong? Because of course our atmosphere is convective. And what we did wrong is that we didn't consider at all moisture in our atmosphere. And so again, here I'll try to be a bit quicker because there's several things that I want to cover. But so now how do we start thinking about moisture in our atmosphere? We need to define how much moisture we have in an atmospheric parcel. And several variables have been introduced. So here now we're thinking of an air parcel that is comprised of a given amount of mass of dry air that I'm going to call M sub D. I'm going to ignore completely here the presence of condensate, and I'm going to just put in there, I'm going to mix into this dry parcel some water vapor. I already put too many dots in proportion. And I'm going to call the amount of mass that exists in water vapor MV, and the total mass of the system M will be given by the sum of the mass of dry air and the mass of water vapor. Luckily for us, water vapor also behaves as an ideal gas, so we can write the ideal gas law for water vapor. And I'm going to write it by using, denoting the partial pressure of water vapor with the letter E. This is standard notation. So again, the ideal gas law for water vapor is just a statement that its partial pressure, E, will be equal to the density of water vapor, just the mass of vapor, mv, divided by the volume of our air parcel, multiplied by the gas constant for water vapor, and temperature. And again, here, I'm just going to write the fact that this gas constant for water vapor is 461.5 joules per Kelvin per kilogram, because the molecular weight is about 18 grams per mole. And then, of course, we also need to consider the fact that we still have dry air exerting its partial pressure. Before, I just wrote P, but of course, now we're thinking about a mixture of two ideal gases. And so to keep this distinction separate, I'm going to rewrite the ideal gas law, just again, emphasizing that now P is the partial pressure for dry air, so it's P dry. And this will have to be equal to the density of dry air, again, MD divided by volume, multiplied by the gas constant of dry air multiplied by temperature. Okay, so now what is one possibility of telling us, introducing a variable that tells us how much moisture there is in this parcel? One of these variables is specific humidity. We denote it by the letter Q, and this is where things get very confusing. We also use dQ to define the change in heat, so it's a mess. There is nothing we can do about it. We just need to make sure that we understand exactly what Q means in the specific context, and we'll see some complications in a minute. So Q, and we're gonna put the subscript V here because you can in fact define a specific content for dry air as well. The specific humidity, QV, is just the ratio between the mass of vapor that exists in the mixed parcel that we're considering divided by the total mass of the system. That is MV divided by M dry plus MV. And then notice how we can define the specific content for dry air exactly in the same way, which is different, smaller than 1. When we normalize by the total mass of the system, I'm going to denote this as Q dry, and this is equal to the mass of dry air divided by the total mass of the system. And notice how it's the sum of the specific humidity plus specific dry air, specific content of dry air, to be equal to 1. The specific humidity is used extensively in, I think, more maybe the European literature. The American literature in general uses mixing ratio. The two are more or less the same, but not exactly the same because the normalization factor is different. And in particular, mixing ratio, which is denoted sometimes by W as vertical velocity. Here I'm using the letter R. Again, with the subscript V is defined as the ratio between the mass that exists in vapor in this mixed air parcel divided by the mass of dry air. Okay? So this is just the difference, the normalization factor. And notice how the mixing ratio for dry air is just equal to 1. Okay? And one can show, again, it's very easy, that the specific humidity and mixing ratios are very similar to one another, but you have the slight difference here at the denominator. But again, all of this we're talking about at most a few percentage in the moistest air parcels. So in general, again, these two are almost the same because the denominator is more or less equal to 1. Okay? Okay, so now we want to write an equation of state for moist air. What do I mean by that? Instead of, again, because the moist air parcel is an entity, right? We want to treat it as an entity. It is clear that, of course, our equation of state will depend on how much moisture there is in the parcel, right? Will depend on the specific humidity, will depend on the mixing ratio, whatever you like the most. And so what I mean by the fact that when we want to write down an equation of state, I just want to write down an equation that looks like the ideal gas law. That is, the fact that pressure and temperature for the moist air parcel are related through density and a gas constant yet to be defined, okay? And again, we'll see that the result is trivial, but let's do it step by step. The result is really trivial. Again, here, we want to write down an equation such that pressure is equal to the product of the density of the moist air parcel and its temperature and a gas constant to be defined. So how do we do it? Very easily, we just use the Dalton's law of partial pressure such that the total, oopsie, I got the wrong, my pen here. So we want to, so we just use, as I said, the Dalton's law of partial pressure, just that the total pressure P is equal to the sum of the pressure of dry air plus the partial vapor pressure. I'm going to use the ideal gas laws for the two. If you remember, we had this density, the product of density and the gas constant for dry air and water vapor multiplied by temperature T. And so now I want to pull out the density rho of the moist air parcel. So I multiply and divide by rho. So we get rho, and then we have rho dry divided by rho multiplied by R dry plus rho vapor divided by rho multiplied by R vapor multiplied by temperature. And I hope that everybody can see that this is nothing else but the specific content of dry air. This is the specific humidity. So this is equal to density multiplied by Q dry R dry plus Q vapor R vapor multiplied by temperature. And this is it, right? We're here. If you just now denote this as R, and I'll comment on what this is, let me call it R tilde. I can rewrite the ideal gas law simply as P, and total pressure equal to the density of the moist parcel multiplied by this gas constant multiplied by temperature, where note how the gas constant, rho tilde, is nothing else but an average of the two gas constants of the constituents gases weighed by their specific content, right? It's very simple. In fact, this is how we derive the gas constant for dry air, for that matter. I didn't do it, but it's exactly the same result. And Q dry R dry plus Q vapor R vapor. I'm gonna rewrite it using the fact that Q dry is equal to 1 minus Q vapor. I'm just gonna rewrite the end result by using the fact that of course the ratio of the two gas constants has a specific value. One can show that this is just equal to the product of the gas constant of dry air that multiplies 1 plus 0.61 multiplied by the specific humidity. Again, here I use the fact that the ratio between the gas constant of dry air and that of water vapor is equal to 0.622. And this, it appears often enough in thermodynamic relationships that we give it a specific letter, epsilon. Okay? Okay, so we could be done, but we are not done because we actually do not like to have a gas constant which is not a constant. Because notice how the specific value of this effective gas constant would be different for parcels that have different specific humidities. We don't like that. We want a gas constant which is a gas constant. And so how do we do it? Let me rewrite this first law of thermodynamics in the following way. Again, rewrite it as P equal to the density of the moist parcel multiplied by the gas constant of dry air that multiplies 1 plus 0.61 QV multiplied by temperature. So the way to do it is to lump this term that depends on the specific humidity on the temperature and define yet another temperature variable that we call the virtual temperature so that we can write the right-hand side of this ideal gas law as the product of the density of the moist parcel, the gas constant of dry air multiplied by the virtual temperature TV, such that again, TV, the virtual temperature, depends not only on the temperature but also on the moisture content of this air parcel through this definition. And I hope that everybody can see, first of all, how for any specific humidity in the air parcel, for any moisture in the air parcel, the virtual temperature is larger than the actual temperature. And this is the temperature that dry air needs to be at to have the same density at the same pressure as moist air. And because water vapor is lighter than dry air, then this temperature needs to be larger. Okay? Let me also emphasize how we could derive, the derivation would be a little bit more convoluted, a virtual temperature also in the presence of liquid water, for instance, cloud droplets, if you think about a saturated air parcel, and you would have a correction term that would depend here on the specific content of liquid water with the minus sign, because of course the presence of it's a water loading effect that makes the air parcel heavier or denser. Okay, when we think about, of course, convection, we cannot not think about a parcel possibly reaching saturation and therefore condensation. And so here, super quickly, What is saturation? Basically, the important point that I want to emphasize here is that pressure exerted by vapor just at saturation with its liquid phase is just a function of temperature through the very well-known Clausius-Clapeyron relation. And so at saturation condition, what you are saying here is that the vapor pressure exerted by, the partial pressure exerted by vapor at saturation condition is just a function of temperature T. And the Clausius-Clapeyron relationship is basically just telling us how that saturation vapor pressure depends on temperature. In particular, it's a fundamental physical law on the derivative in respect to temperature of the logarithm of the saturation vapor pressure. That is 1 over ES dES dt will depend on temperature in the following way. It will be equal to the latent heat of vaporization divided by the gas constant of water vapor and temperature squared, with again the latent heat of vaporization being equal to 2.5 10 to the 6 joules per kilogram. This is just telling us that we need this many joules to evaporate 1 kilogram of water. The same energy is released when 1 kilogram of water vapor condenses out. And here, let me just write down a very useful approximation for typical atmospheric temperatures. When you integrate this, ES of T, again, this is somewhat approximate, is just equal to constant multiplied by the exponential of beta T. So here really the important thing is that basically the saturation vapor pressure is a very strongly nonlinear function of temperature, and in particular increases exponentially with temperature. And let me write down here the values of the constants that appear in this specific simple approximation. A here will be equal to 6.11 hectopascal, and beta is equal to 0.067 per degree Celsius. I always tell my students, whenever you see some formulas, for instance, for the saturation vapor pressure, just be sure, look at the units. This works for temperature in degrees Celsius. And this constant A here just represents the saturation vapor pressure at the freezing point. It would be different. It's definitely not absolute zero. Okay, so always be careful when you use this thermodynamic formulas. We can, of course, define saturation-specific humidity. This is the specific humidity of a parcel that is just at saturation. I'm just going to give you an approximate form. I'm going to denote this as QS. Again, this is basically the maximum amount of water vapor that can exist in a parcel. If you have more water, the excess relative to this saturation value needs to be in the liquid form. Oh, again, could also be ice. Here I'm just talking about the liquid phase to make things simple. Also because all of this thermodynamics is based on equilibrium arguments. And when we have ice, we are very far from equilibrium, among other difficulties. So again, what is the value of the saturation specific humidity? I'm going to assume that this is more or less equal to the value of the saturation mixing ratio. And one can show that this is equal to epsilon, this ratio between the dry gas constant and the gas constant of water vapor multiplied by the saturation partial pressure, water vapor pressure, divided by the actual pressure of the parcel that we are considering. So while the saturation vapor pressure is only a function of temperature, the specific humidity of a parcel at saturation is both a function of temperature and pressure. Although, as you can see, the dependence on pressure is just inversely linear. The dependence on temperature is exponential through the Clausius-Clapeyron relationship. And here I'm just showing, this is stolen from Hartmann, Global Physical Climatology. On the y-axis, we have saturation vapor pressure. on the blue axis, saturation-specific humidity. And again, for instance, go back to the approximate formula I gave you before. At the freezing point, the saturation vapor pressure is about 6.11 hectopascal. Okay, before we move forward, let me show you what the specific humidity looks like. Oh, no, before I do that, sorry. Let me define the relative humidity, because I haven't done it yet. Again, specific humidity is also an absolute, a statement of absolute humidity, right? How much absolute moisture we have in an air parcel. But sometimes we are interested in knowing how far or close we are to saturation. And so that's where we introduce the relative humidity. And the relative humidity is defined as the ratio between the actual vapor pressure in the air parcel that we are considering divided by the saturation vapor pressure, the pressure you would get if the parcel were saturated in respect to its liquid phase, and this is expressed in percent. And now I'm going to write, again, this is an approximate expression, but it's very useful to understand the plots that I'm going to show you in a minute. We can show that the specific humidity is more or less approximate. So this is the actual amount of water vapor normalized by the total mass of the air parcel that you have in an air parcel. This is approximately equal to the relative humidity multiplied by the saturation specific humidity, the amount of water vapor that would exist at the temperature and pressure of the air parcel if the parcel would be just at saturation. And in fact, this statement is very simple. For relative humidity equal to 100%, the amount of water vapor that you have in the air parcel is just equal to the saturation amount. I wanted to introduce this because I want to show you what the distribution of the specific humidity is observed in the meridional plane. Again, as before, for each latitude, we average in longitude, and then we look at the distribution of the specific humidity as a function of height or pressure and latitude. This is for the annual mean, Northern Hemisphere winter, Northern Hemisphere summer. Notice how these plots have a logarithmic scale. So relative humidity changes by several orders. Sorry, did I say relative? Specific humidity changes by several orders of magnitude, both as we move higher up and as we move away from the equator. And this is the distribution in DJF, and this is the distribution in JJA. I don't think I have a distribution of temperature, but if you were to look at the temperature distribution in the meridional plane, you would see that there is a strong relationship between the distribution of specific humidity and that of temperature. And I'll try to explain to you why that might be the case in a second. That is to say that the distribution of the specific humidity is strongly controlled by the thermodynamics. If you know temperature, you more or less know what the specific humidity is. Let me show you the distribution of the relative humidity. Again, annual mean, Northern Hemisphere winter, Northern Hemisphere summer. Notice how, of course, relative humidity does change, but it changed just by a few percentage points, much less than the specific humidity does. What controls these patterns of the relative humidity is still very much an open question in the field. Let me emphasize, there's several points that I want to make. Let me emphasize how, if you look at the boundary layer, here let's just say 1 kilometer below the surface, from the surface, notice how the relative humidity is relatively constant, right? I mean, it changes, but it doesn't change by a whole lot. We're talking about 60, 70, 80%, regardless of whether you are over the tropical oceans or you are in the subtropics or at higher latitudes. We also see that in general relative humidity, it's not quite constant in the vertical direction, but it tends to be high where we have the ascending branch of the Hadley cell. This is something that I think Spencer will talk about later on. And then we have these pockets of dry humidity, of low relative humidities, these dry regions that are basically in the mid-troposphere under the descending branches of the Hadley cell. So this is to say that while specific humidity is more controlled by thermodynamics, relative humidity is controlled by both thermodynamics but also dynamics. And why? Because in reality, again, there are models that have been built based on these arguments. You can think about the relative humidity. You could trace it back to when a parcel last reached saturation, and then you need to follow its motion. But here, the important point that I really would like to emphasize is that relative humidity does not change much, both if you look at the spatial distribution of it, if you look at its evolution through the seasons, whereas specific humidity changes much more. And then if we go back to our definition of the relationship between specific humidity and the saturation specific humidity through the relative humidity, if you assume that the relative humidity remains more or less constant, you see why specific humidity is strongly influenced by thermodynamics through the basically Clausius-Clapeyron relationship, through the dependence on temperature and pressure, but to a, of course, lower, less strong dependence. It's really strongly connected to the temperature patterns. Okay, and let me emphasize how relative humidity also remains somewhat constant through climate change. And in fact, the very first calculation of the equilibrium climate sensitivity, that is the temperature change, if we were to double CO2 concentrations made by Manabe and Weatherall in 1967, which basically work that for which Suki Manabe was acknowledged with the Nobel Prize in Physics in 2021, he made the first calculation assuming not that what would remain constant under climate change is not specific humidity, but relative humidity. And in fact, if we assume that relative humidity stays constant, specific humidity increases strongly with increasing temperature, giving rise to what we call a water vapor feedback. Okay? So these are all important points that I wanted to emphasize. Dave also asked me to introduce precipitable water or column water vapor. There's many names. And this is the distribution. These are all based from ERA. This is, I think, ERA interim, annual mean, DJF, JJA, and basically this is the vertical integral of water vapor, and this is expressed sometimes in terms of depth. It's said as the units of length. This would be the depth of the liquid water that you would get if you were to spread all of the water vapor, if you were to condense it out and spread uniformly on the surface of our planet. And again, on the global mean, notice we're just talking about 24 millimeter of water. Okay, not a whole lot of water out there. Okay, so this I hope introduced a few important variables, also a few important concepts that probably we'll touch upon later on in the next 3 days. And so then the question is, what happens if we take an air parcel from the surface, which is subsaturated, but not too far from saturation, and we lift it up? So again, let me go back to my very simple schematic. So here, my y-axis will still be z, our vertical coordinate, the height from the surface, and this is the surface. We are somewhere, and here I'm still thinking about how temperature of an air parcel would change if you were to lift it up. And so we're thinking about an air parcel that starts from the surface, and I'm going to assume that this air parcel has a relative humidity of 80%. Why 80%? Because again, if you were to go back, we saw that this is a typical value of the relative humidity, for instance, close to the tropical ocean. And so let's assume that, again, we start with this value of the relative humidity. Of course, we would need to know the temperature of the air parcel, actually the surface pressure. We assume it's 10,000 hectopascal, but it's not, of course, always like that everywhere. And so I'm just saying that I'm just going to introduce the specific humidity value, QV, of the air parcel at the surface. This is where the parcel is starting from. And let me emphasize that because at the surface the parcel is subsaturated, what this means is that its specific humidity is smaller than the saturation value at the surface temperature and pressure. This is the definition of a subsaturated air parcel that has a relative humidity smaller than 100%. So this is, the parcel is subsaturated at the surface. Okay, so what happens if we lift this air parcel up? As we lift this air parcel up, we know that it will undergo, and again, here we're still using the same assumptions. We assume that the parcel goes up adiabatically, and so it will expand because it finds itself at lower pressures, and so its temperature will decrease. And until the parcel reaches saturation, to the degree that the parcel remains subsaturated, the rate at which temperature decreases is still the dry adiabatic lapse rate. In reality, there is a small correction, which we don't want to worry about, but it basically goes up dry adiabatically until it reaches a height where its temperature has decreased to a point that the specific humidity the parcel started from becomes equal to the saturation specific humidity at that temperature and pressure. We call that level the lifted condensation level. If we keep lifting, and then I'm going to write this all, I'm going to fill the schematic in a minute, just let me say this in words. If we keep lifting the air parcel up, the temperature will decrease. What this means is that the saturation specific humidity will keep decreasing. Now the parcel has more water vapor that can exist in the vapor phase, and so the excess water vapor will have to condense out. And this is how a cloud is formed. The other important thing is that as the parcel goes up and water vapor condenses out, now part of the work that the parcel is doing through this expansion and at the expenses of its internal energy, so the rate at which the temperature decreases, will be compensated for by the latent heat that is being released when water vapor condenses out. So beyond the lifted condensation level, the rate at which the temperature of a parcel, once it has reached saturation, decreases with height, will be smaller than the dry adiabatic lapse rate. The temperature decrease will be less fast than the dry adiabatic lapse rate. Okay, let's try to put all of this together in this schematic. So again, before the parcel, or below its lifted condensation level, the parcel will still go up following a dry adiabatic lapse rate. Again, I'm going to denote this as gamma dry. Then once it reaches its lifted condensation level, and of course we need to know both the temperature, the pressure, and the actual value of the specific humidity to determine the lifted condensation level. Then once it reaches the lifted condensation level, at the lifted condensation level, again, I'll write it down in a second, this is where the amount of the specific humidity with which the parcel started from at the surface is exactly equal to the saturation specific humidity at the height and pressure of the lifted condensation level. And beyond this level, the rate at which temperature decreases, sorry, I wanted to use another color, the rate at which the temperature decreases is smaller than the dry adiabatic lapse rate, and we call this the saturated lapse rate to emphasize that this is the rate at which temperature decreases following a saturated ascent. The parcel is saturated. Okay, let me try to summarize this. I'll write this all down. So as the parcel goes up, again, we're starting from the surface now. It gets closer and closer to saturation until it reaches its lifted condensation level. What we call the LCL. Where again, the LCL is defined as the level at which the initial specific humidity QV is equal to the saturation specific humidity at the temperature and pressure of the LCL. Let me try, well, follow what I say and then you'll see it written, as then I'll share the slides later on, as the parcel is raised beyond its LCL, the excess water vapor will have to condense out, and the associated latent heat release will partially offset the adiabatic cooling. I hope I couldn't see what I was writing, so I'm sure there's going to be gazillions of typos. Let's see what I wrote there. Okay, as the parcel is raised beyond its LCLs, the excess water vapor, well, I'll correct this later on, will have to condense out, and the associated latent partially offset the adiabatic. Uncooling, that's not uncooling, okay? And hence the rate of temperature decrease, at the rate at which temperature decreases in a saturated acid is smaller than the dry adiabatic lapse rate. I'll share with you the slides, so don't worry, you'll get them later on, free of any typo. Okay, so now we want to introduce quantities that are the moist conserved, that are the moist equivalent of the conserved quantities that we introduced early on. Remember, we talked about enthalpy, dry enthalpy conserved under the assumption of adiabatic and isobaric process. We talked about dry static energy under the assumption of adiabatic acid in which pressure changes hydrostatically, and we talked about entropy or potential temperature as the variable that is conserved under the more general assumption of just and isentropic displacement or vertical displacement. So now we want to define moist quantities that are conserved in a specific transformations that are the moist analog of conserved quantities in dry thermodynamics. And the way I'm going to do this here today is not the most accurate way, but it's the easiest one. So that's what we're going to do. And so what we're going to do, we're going to modify the first law of thermodynamics to account for the fact that when we lift an air parcel up, as we just described, we are still assuming that it's adiabatic in the sense that it does not exchange heat with the environment, but we allow for water phase changes. We allow, for instance, for an air parcel to go up adiabatically, and once it reaches saturation for water vapor to condense out, if we were to bring it down, then all of the liquid water will evaporate because the parcel will compress. It finds itself at lower pressure. Okay? So how do we do this? Again, this is still adiabatic. It's adiabatic in a moist sense, in the sense that water vapor, water phase changes are still considered as internal to the parcel. It does not arise with the fact that the parcel is exchanging heat with the environment. In fact, we are assuming, as you assume adiabaticity for this parcel, we also are going to assume that water, it's going to remain constant. The amount of water in all of its phases remains constant in this air parcel. It will just have to transition between phases. It will just have to change phase depending as to whether it has reached or not saturation. Okay? Is this clear? Okay, so how do we do this? Again, let me rewrite, and this is, as I told you, that things were gonna get messy a little bit with the notation. And so again, let me rewrite the first law of thermodynamics. We're gonna say, okay, Cp dt minus 1 over rho dp will have to be equal to the heat that is being exchanged with the environment. Now we say, okay, the parcel does not exchange any heat with the environment. So in that respect, the Q is equal to 0. So for instance, we don't allow we're not assuming, so we're, for instance, thinking when an air parcel goes up, that it goes up on convective timescales that are much faster than radiation timescale, so the parcel doesn't have time, for instance, to lose energy through radiation. But what we're going to say is that we're going to account for the latent heat that is being absorbed or released when water vapor evaporates or condenses out. And so we're going to route this dq. And again, here, this dq is the heat that is released or absorbed to allow for water phase changes. And we're going to say, okay, so this, of course, will have to be proportional to the change in the specific humidity. And so this dqv represents the change in the specific humidity of the air parcel as we're lifting it up or down. And then, of course, we need to transform this in units of energy. So we multiply it by the latent heat of vaporization, and we put a minus sign here. Why the minus sign? Because, for instance, when water vapor condenses out, the specific humidity decreases, and that will release latent heat. So we get a positive dq. Okay? So now let's therefore put now this term, bring it on the, this term on the other side, so on the left-hand side, and therefore we can rewrite the first law of thermodynamics such that Cp dt minus 1 over rho dp plus Lv dqv, again dqv is the change in specific humidity, will be equal to 0. Okay? And so notice how now, in this way, what we are just saying is that when we are thinking about an adiabatic expansion of a compression or a moist air parcel, in addition to the exchanges of energy that we saw in dry thermodynamics between dry static energy and potential energy, we need to account for an additional source of energy, which is the latent energy. It's latent because it only manifests itself once water can undergo phase changes. But it's internal to the parcel. It's this potential energy that can be released if the water vapor that exists in the air parcel condenses out. Okay, so it's not exchange of heat with the environment, it's an internal form of energy that we need to account for in moist thermodynamics. And so now, super quickly, so now we can define the equivalent, and again, you'll see that. Again, I'm going to give you here just the definitions, but it will become clear why we write these variables the way we do. So we can define moist enthalpy, which is the equivalent of enthalpy, is just the variable that is conserved under an adiabatic and isobaric process. Again, we already wrote here the first law of thermodynamics, assuming adiabaticity, in the sense that there is no heat exchange with the environment. If there is no pressure change, then I hope that everybody can see that now the moist conserved quantity, which is the equivalent of enthalpy, and I'm going to write it with the subscript m, h, remember we used h for dry enthalpy, is equal to dry enthalpy CPT plus this additional latent energy term that is associated with the presence of moisture in the parcel. I am not going to do it, but again, hopefully it's very straightforward to show that exactly in the same way, we can now define a moist static energy that is also conserved like the dry static energy under an adiabatic process in which pressure changes hydrostatically, but this is the degeneration to a moist air parcel. Again, I'm going to use the same letter S, although later tomorrow, you'll see that I'm going to talk about moist static energy with the letter H. Again, sorry about that. As I mentioned, there are more variables than there is letters in the alphabet. And so the moist static energy is equal to the dry static energy, CPT plus GZ, plus this latent energy, LV, QV. Okay? Notice how these variables are defined just as the dry counterparts, but now latent heat due to water phase changes is considered another energy form that participates to these energy transformations. Okay? And then I don't have time to actually define moist entropy. It's a very similar generalization. It's just a little bit more complex. In fact, I didn't even define, well, no, I did define dry enthalpy dry entropy in terms of potential temperature. But let me just say that the concept of a moist entropy that is conserved under just the assumption of an adiabatic process without, for instance, making any specific assumption as to how pressure changes, provides the basis for the definition of yet another temperature variable that we call the equivalent potential temperature, which is the temperature that an air parcel would reach if we were to bring it adiabatically to a reference state P0. But now we are in a moist world. And so we need to, that is to say, this reference state is not just defined completely and uniquely by the pressure value. We need to decide what we're going to do with water. And so the equivalent potential temperature is the temperature that a moist parcel would get if we brought it adiabatically, in a moist sense, to a reference state with a given pressure P0 in which all of the water vapor has been condensed out. There is another variable, because you can imagine now that you can define an infinite number of these reference states, where, for instance, you have half water, half liquid, half vapor, half liquid. And in fact, we don't define an infinite number of these equivalent potential temperatures. There is another one that is used in the literature that is defined exactly in a similar way, in which we bring an air parcel adiabatically to a reference pressure P0, in which all of the liquid water that you might have had in the parcel at the beginning is evaporated. Okay? And so I'm going to give you an approximate definition of this equivalent potential temperature that is equal approximately to the actual potential temperature, to the dry potential temperature, multiplied at the exponential of LVQV divided by CPT. And the important thing is that for any water vapor, any, moisture in the parcel, the equivalent potential temperature is larger than the dry potential temperature. Okay? And again, why do we have this exponential factor? Why is equivalent potential temperature larger than potential temperature? Because you're condensing all of that water vapor that you had. And that gives rise to this additional form of energy that is being released within the parcel and therefore manifests with a larger value in the equivalent potential temperature. Okay, so there is a couple of things that I want to do. We started a bit late, so maybe I can go until 11:05. Okay. I just want to super quickly give you just again the basis, then do it yourself, of how we might go and derive an expression for the saturated lapse rate. Again, here saturated means that it's the rate at which temperature decreases once the parcel has reached saturation. And the way we do it is we use, as we did for the dry adiabatic lapse rate, the first law of thermodynamics, but now we are, of course, allowing for the presence of latent energy. And so what is conserved is not the dry static energy, but it's moist static energy. So the differential of CPT plus GZ plus LVQV will be equal to 0. And then once we have reached saturation, and that's a very important point, the specific humidity of the parcel is constrained by the saturation specific humidity. The parcel cannot have more moisture than the one that can exist at saturation. So once the parcel is saturated, the change in the specific humidity is constrained to be equal to the change in the saturation specific humidity. And let me here emphasize how the saturation specific humidity is a function of temperature and pressure. It's not now another independent variable. Once you know temperature and pressure, you know exactly how much moisture can exist in the parcel at saturation. I'll skip the details here, but again, just do it. You have all of the ingredients to do it. Go back to the definition of the saturation specific humidity, and you can show that the saturated lapse rate, that is the rate at which temperature changes in an ascent in which the parcel is saturated, is going to be equal, I'm going to write the end result, it's going to be a bit messy, is going to be equal to G over Cp. If you remember, this is the dry adiabatic lapse rate that multiplies this ugly thing, which at the numerator has 1 plus LVQS, which is a function of temperature and pressure divided by R dry T divided by 1 plus LV squared QS temperature and pressure divided by CP RV T squared. Okay? And so here, really the important points that I would like to emphasize, I'll let you guys, I see people still maybe copying. The one point that I really would like to emphasize, which is summarized here, I had an extra slide, is that two important points about the saturated lapse rate are that it's not a constant, but changes with height. And one important point here is that you need to, I mean, this is not determined a priori. You need to know the humidity, the temperature, the pressure from which the parcel started from, and after you determine the lifted condensation level, you need to compute it, iterate it in an iterative way, because the temperature that appears here is the temperature of the air parcel. But the important point here is that, again, it's not a constant with height. It changes, and it is always smaller than the dry adiabatic lapse rate for physical reasons that we already introduced. And again, this varies with height, but on average, the saturated lapse rate, when you are a little bit away from the lower levels in the troposphere, is about 6.57 Kelvin per kilometer. Okay, so this leads me, and I'm almost done, there is just 2 more points that I want to make. This leads me to the concept of conditional instability. And what do I mean by that? We're still thinking about an air parcel that goes up and thinking about, about whether it will be positively or negatively buoyant if we lift it up. And we discussed the dry case, but now in the moist case, there is this ambiguity. Are we thinking of an air parcel that is unsaturated, or are we thinking of an air parcel that is going up saturated? Because the rate at which temperature decreases for an adiabatic expansion will be different if the parcel is dry or if the parcel is saturated. And this gives rise to this concept or of phenomena of conditional instability that I'm going to try to summarize quickly here. So again, here I'm still thinking about my thermodynamic diagram where my y-axis is height, this is not going to work, okay. My x-axis is temperature. Let me try to go a bit more straight. Okay, great. So I'm still, but now I have 2 fundamental lines. Fundamental lines are the lines that we use to describe these adiabatic processes that we assume the parcel undergoes when we displace it up or down. Again, I told you that the saturated lapse rate is not constant. I'm going to, again, just assume it's constant because it's easier to draw this on a thermodynamic diagram. So this is the dry adiabatic lapse rate that I had before. And this would represent, again, this line represents the rate at which temperature decreases if we lift an unsaturated parcel up. But we also have this additional fundamental line now that describes how temperature changes or decreases with height if we lift an air parcel that goes up saturated. Okay? And this is my gamma S. Okay, so another question is, again, an atmosphere stable or unstable to vertical displacement? Well, we need to decide whether we're talking about a saturated or unsaturated vertical displacement. I hope that everybody can see that because the gamma dry so the dry adiabatic lapse rate is larger than the saturated lapse rate. If the environmental lapse rate is to the, this diagram, is to the left of the dry adiabatic lapse rate, what this means is that if the rate at which temperature of the environment decreases is faster than the dry adiabatic lapse rate, we talk about absolute instability. And that is because the parcel will always be warmer than the environment, right? Again, I'm going to do this super quickly. Let me now, this will be, and again, I'm going to do it just for absolute instability, not absolute stability. But if this is now my, sorry, I didn't want to do this. I wanted to do this. If this is the temperature profile of the environment, if now I take an air parcel up from the surface, regardless of whether the parcel goes up unsaturated or saturated, it will always be warmer than the environment at that height. And so this is absolute instability. For the same reasons, for all of the environmental lapse rates such that the corresponding curve is to the right of the saturated lapse rate, we talk about absolute stability. And that is because regardless of whether the parcel goes up saturated or unsaturated, it will always be colder than the environment at the same height, and so it will sink back. But now we have this situation, again, this interesting situation that did not arise when we were thinking about a dry air parcel, where the environmental lapse rate is larger than the saturated lapse rate, but smaller than the dry adiabatic lapse rate. And in this case, then again, we have to decide if we're thinking about lifting an air parcel up, saturated or unsaturated. Because, again, if this is now the environmental lapse rate, if we lift an air parcel up unsaturated or dry, it will find itself colder than the environment, and so it will be stable. But if we lift an air parcel up saturated, it will find itself warmer than the environment, and so it will be unstable. And that is why we talk about conditional instability, in the sense that instability is conditional to the parcel going up saturated. So super quickly, I'm going to summarize this here. So if the environmental lapse rate, gamma E, is larger than the dry adiabatic lapse rate, which is larger than the saturated lapse rate, we have absolute instability. If the environmental lapse rate is smaller than the saturated lapse rate, which is smaller than the dry adiabatic lapse rate, we talk about absolute stability. And if the environmental lapse rate is larger than the saturated lapse rate, but smaller than the dry adiabatic lapse rate, we talk about conditional instability. Conditional to the parcel going up, saturated. And conditional instability also implies the existence of a finite amplitude instability that I think Adrian will touch upon. Right, Adrian? You'll talk about finite amplitude instability, CAPE, and the likes. Yeah, so I can skip that. And if I'm allowed 2 more minutes, I was going to go through the Clausius Clapeyron scaling. But if I need to stop here, I'll stop here. We're done? You guys are done? Okay. I'll bring it back in another lecture.
Yeah, you can, I would say your next one, maybe start with that one.
Yeah, I'll start with
Okay.
that.
Also, we wanted to leave people the opportunity to ask questions. So if you can attack her during the break right now. You can grab her and question her. So we'll be back well, I guess it's right out here. I haven't seen where they actually set up the coffee. It's just outside? Oh, back here, behind us? Oh, okay. And so try to be back by 11:30, right? 11:30? And then at Adrian. Make so much noise.
full presentation actually, so I'm slightly concerned I might overrun. So I will get started. So what I wanted to try and do in this hour is give a very basic introduction to convection, and this really follows on from Simona's lecture this morning. I just wanted to point out, I've got a link there, you'll see, to my homepage. So I've got a kind of set of handouts, which are not as polished as Simona's, but nevertheless, they might be helpful to supplement some of the things I'm showing here, because of course I had to condense what I normally teach in several lectures down into just 1 hour. So my aim today is to just briefly introduce the concept of convection. And I really wanted to kind of start from the surface and work up. And so by the end of the lecture, I wanted to kind of introduce basically, at least just in very brief terms, the different types of convection we might consider and see in the tropics, starting from stratocumulus through trained wind, cumulus convection, and then ultimately deep convection, which we can see in this schematic, which tries to depict a kind of a schematic of the overturning circulation in the tropics associated with the Walker and the Hadley circulations. Okay. So as I said, there are many different types of convection in the atmosphere. This cartoon actually, this snapshot here is actually a direct numerical simulation of basically Rayleigh-Bernard convection, which is just a fluid between two plates, one heated below and the top one kept at a constant temperature, two different temperatures, so you have a temperature gradient. But as I said, I'm going to talk through all these different kinds of convection in this talk and try and introduce them. So hopefully they should become familiar as the hour goes on. So as basically it was already pointed out in Simona's lecture, I mean, convection essentially is any kind of motion that results from the action of the gravitational field on variations in density. Now, as Simona pointed out in her talk, if you actually go through the full derivation, it's in her notes and my notes as well, starting from the momentum equations, that density perturbation can theoretically arise from temperature perturbations and pressure perturbations. But as Simona says, if you do a scale analysis in the atmosphere for flows and movements which are essentially subsonic, much slower than the speed of sound, we can ignore the pressure perturbations, and we assume that density perturbations in the atmosphere basically derive mostly from the temperature perturbations. So when we talk about density perturbations, we're really talking about those that derive from temperature modified by the humidity. We saw the virtual temperature, okay, and we ignore pressure perturbations, which was the fundamental assumption of the parcel. So this is a little kind of snapshot of Rayleigh-Bernard convection. It's like looking at a plate, very small scale, it's heated from below. You've all done an experiment, I'm sure, when you've gone to boil water for your pasta, you put it on the stove. If there's any little bits of like grit or something in the water, you start to see after a while, at first they're motionless and then they start to undergo circulations in your pot of water. Okay, that's you basically simulating Rayleigh-Bernard convection in a pot you're heating from below. Okay. So we can imagine, here's a really simple basic undergraduate textbook where we're heating a fluid from below, we're heating the atmosphere from below. So we have the sun heating the surface, and we have transfer of heat by, for example, conduction to the air, which is warm, and if that air basically is less dense than the surrounding air, then this bubble of air basically forms a thermal. So I actually added, during Simona's talk, this little cartoon, just so how we can think about, she had a diagram where she had her dry adiabat in the vertical. So here we have, this is the vertical direction. And if we can imagine a profile here on the x-axis, we can have the potential temperature or indeed the dry static energy. And if we have a profile, we can imagine, which is slightly unstable, so it's decreasing in height. Remember, Simona said the parcel, if it's lifted and we don't have any condensation, follows a dry adiabat. Then we can imagine this parcel of air, as it's lifted, it's going to be warmer than its environment and will accelerate upwards. Okay. Why would we expect that we might have a slightly unstable profile? Because we're heating from the surface below, and we'll see also that we can have radiative cooling of the layer above. So those processes are trying to destabilize this layer, cooler and warmer, So the parcels of air will react to that by moving upwards, and they'll be acting to warm this layer. And these parcels, if they're perturbed, will be cooler than the environment and move down. So the motions and the warming associated with that transfer of heat by convection will be trying to bring this profile back to neutrality. Okay. So that's what Simona was talking about when she talked about stability. Now, if we actually kind of zoom down into smaller scales, okay, start off, let me just click on here. Actually, at very small scales close to the surface, the picture is a little bit more complicated. The air molecules in contact with the surface are completely motionless, okay? And within a few millimeters of the surface, essentially, the air is so viscid at those small scales that the motions will be laminar, not turbulent, and will be very inefficient at working against the heating. So we have this laminar layer, in fact, in the first few millimeters, which has a very, very strongly super adiabatic profile. In other words, the temperature over those few millimeters can already drop on the order of 1 or 2 Kelvin. Okay. And then above that, as we start to move away from our surface, in the lowest 5, 10, 20 meters, we have a transition layer, which we call the surface layer, where the air starts to become turbulent, but it's still not efficient at removing the instability. Okay. So then that surface layer, which on this kind of cartoon is kind of nearest order of magnitude, they actually have it kind of up to 100 meters. It's usually less than that, on the order of like 20 meters or so. Basically here, turbulence is not efficient enough to remove that destabilization. And so you'd still tend to have a super adiabatic profile where the temperature can drop about 2 Kelvin over those 20 meters in what we call that surface layer. Okay. Once we get above that, over the scales of the eddies, more than 20, 30 meters, they become efficient enough that they can then essentially keep the profile close to dry adiabatic. Okay. So it's only above the scales around 20 meters that the turbulence becomes efficient enough. And that's because at those scales, essentially, the air can be considered to be inviscid. Okay. So I'm going to come back to this again and again when we come to like deep convection and so on, that we have processes that are trying to destabilize, heating from below, cooling from above, and they can be slow. And then the air basically reacts to that instability by the turbulent motions, which tend to be very fast processes. They're very efficient because the air at those scales is inviscid. We can imagine turning the air into like a big treacly mass, like the honey I put on my cereals this morning at breakfast. That would be much less efficient at removing those instabilities, and we wouldn't have these dry adiabatic profiles. So if we look at a profile now, I apologize that this is a little bit of a grainy plot, but basically on the x-axis here we have temperature, and on the y-axis we have height, just like Simona showed in her lecture. And this is an actual radio sonding ascent in Holland, at a place called Cabo, in the afternoon. Okay, local afternoon. Why can we tell it's local afternoon? Okay, does anybody know why we can tell this is local afternoon and not 5 a.m. in the morning? Does anybody have an idea? When I give my lectures, actually, you're going to have to get used to this. I know we only have an hour, but I'm going to shout out. Am I speaking too quickly, by the way? Is it okay, the speed? Okay, great. So we can tell it's the late afternoon because we're having heating from below, and the profile of the temperature that we measure is very close to that dry adiabat. This is dT by dz is minus 9.8. It's not showing very well on this plot. What is that 9.8, minus 9.8 Kelvin per kilometer? What was that relevant? What is that slope that Simona introduced in her lecture? Does anybody remember? That was you can all shout out together. Don't be shy. It's the dry adiabatic lapse rate, okay? So we can imagine, and look here, notice this slope in the lowest meters where the temperature is dropping off much quicker. This is that surface layer where the turbulence is not very efficient. If you imagine a parcel of air here, if we take a temperature that's slightly perturbed, it's going to follow its dry adiabatic lapse rate. It's always going to be warmer than its environment, warmer, 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 until we reach here, where we have a strong inversion. Okay, the parcel will have positive momentum. Okay, it's going to basically overshoot, maybe mix with some of the air in the inversion transition layer, or even above if it's able to overshoot enough, and then sink back down to this layer, warming this layer. The same way parcels here will sink following a dry adiabat, will act to cool. So because this is heated from below this layer, it's close to dry adiabat. We'll see in a moment, at night, it looks very different. Okay? So this is dry turbulence driven from heating from below. Okay? So here I've drawn on this line of a kind of hypothetical parcel. It's overshooting, it's mixing in this transition layer and then sinking back down. Specific humidity in these motions is also conserved. Think back about the definition of specific humidity and or the mixing ratio that Simona introduced. Okay? The mass of the water vapor divided by either the mass of the dry air or the total mass of the moist air. Okay? That mass of water vapor is conserved in these motions. So because the layer is turbulent, we can see that through the layer, we have almost a constant specific humidity measured in the environment because those motions are mixing. It's like I could take, imagine if I release the gas in the corner of this room, okay, then I have a gradient. But if I take a giant spoon and mix up the atmosphere, eventually it'll be completely well mixed. And no matter where I measure the content of this gas, it'll be equal everywhere. It's the same here. The humidity is being mixed up. Apart from this little feature here, I'm not going to stop because I have a limited amount of time, but think about what this might be. This, okay? We can talk about it at lunch. Okay. Oh, sorry. I wanted to ask a question. If the specific humidity is fixed, okay, and we have a dry adiabatic lapse rate, what is the relative humidity going to be doing in this layer? Is it going to be increasing with height, decreasing, or will it also be conserved and constant? What will the relative humidity do as we go up in the atmosphere? And you should know this directly from Simona's lecture before. So what will the saturation value be doing? Remember, we said about the saturation value, and Simona introduced the, so it's the temperature. What is the temperature doing as we're going up in the boundary layer? It's decreasing. So what's happening to the saturation specific humidity or the saturation mixing ratio as we go up in the boundary layer? It's also decreasing, okay? And this is fixed, so the ratio will be increasing. So we can see that relative humidity, and I have to click here, is going up. So above the surface layer, the relative humidity is increasing, okay? Here it's about 75%, here it's almost 90%. Okay, so in a moment we can see when we hit the inversion, what happens during the day if this layer gets deeper and deeper and we can continue to extrapolate? What's going to happen eventually to the relative humidity? It's going to hit 100%, yes? And at that point there, as we know, we basically have condensation onto droplets. We don't have time to introduce all the microphysics. It's not actually obvious that that happens. You can, in theory, have supersaturated air, but because of the presence of aerosols, it actually means that we have surfaces on which to condense all the excess moisture onto droplets. Okay, there we go. Okay. So this is from a textbook by Stoll, and it kind of then illustrates what we expect. So this summarizes what we've seen so far, and basically it shows idealized profiles of. We can just imagine this to be potential temperature. It's actually the virtual potential temperature. So Simona introduced the virtual temperature, for example, in her talk. And we can see that it's basically, this is the surface layer, then it's fairly constant, and then we go through the inversion. And this is our transition layer. And this is our humidity, so specific humidity, and it's basically fairly well mixed, and then it's going down. Okay. Question, if you look at these two profiles, the potential temperature seems to be much more constant than the humidity, where we've got a little bit of a gradient. Why do you think that is? Does anybody have an idea? Why is it that we have more of a gradient in humidity in this idealized profile than we do in theta? Say again? Not exactly. Have a look at what's happening above the boundary layer. If we look here, we have heating from below. What happens to the potential temperature above the inversion? it's increasing. What happens to the humidity? Usually it's much drier. Okay, so we're heating from below, okay, but when we have the turbulent entrainment at the boundary layer top, we also bring higher theta air into the boundary layer. So it's increasing from above and below. Instead, for the humidity, we have dry air above. So when we have overshooting and turbulent mixing that deepens the layer, we also bring drier air into that boundary layer. So that means we're drying from above, but moistening from below, especially if we're over a saturated surface such as the ocean. Okay. So the theta is warmed from above and below, but the humidity is dried from above and moistened from below, which is why we have a slightly greater gradient there. So here we have, I thought, well, let's have a little bit of fun. Let's look at a radio sonde from Mexico. So this is last week, 17th of January, and this is Guadalupe. So you'll all know much better where that is than me. I remember picking it out on the map, okay. And so this is what was happening last week. If you search me and you go to my current weather page, I have lots of links, and there's a link where you can go to a site from the University of Wyoming and look at the radio sondes. If you've not done that before, and you're just starting out especially, I encourage you to do this. If you have a boring moment, instead of going and watching, I don't know, something on YouTube, which is not a lecture, but like a thing, I encourage you just to spend your 5 minutes relaxation surfing around the world at radio sondes, okay? It's like, or looking at satellite data. Because you learn a lot about difference in meteorology around the globe by looking at radio sonde sites. So look what's happening here. This particular site sounding here, what do we see at the boundary layer? Look at the temperature, and these are lines of constant theta in green on this skew log T. Remember, these blue lines are pressure. We're going up in the atmosphere, if you're not familiar. So this green line is a line of constant theta, and look at the boundary layer. It's an absolutely perfect world mixed layer. We've got a little bit of a reflection in the humidity, but these purple lines are constant humidity, constant mixing ratio. And basically, we can see that we're close to a well-mixed line, okay? And in fact, at the top here, these two are actually touching. So what does that tell us? We actually have saturation. So at the top, this situation here, I suspect that that day they had some fair weather cumulus clouds, okay? Because they had condensation because these two lines mixed. And then we have this beautiful inversion at the top of the boundary layer. Okay, so those idealized profiles are real, you see them, okay, and I strongly encourage you to do a little bit of surfing and have a look around. Quick mention of the diurnal cycle, okay, this is very old, this profile, again, I think I took this from Stoll, and it just shows the patterns during the day. So during the day we're heated from below, again we have this dry adiabat, but at night, of course, that heating is cut off over land, and we have radiative cooling to space, so the surface temperatures drop off. So at night, you can see that we actually have a very stable layer. Okay. So theta is increasing strongly with height. This is air temperature. This is my dry adiabatic slope. Okay. So theta will be strongly increasing in height here, and we have this stable layer. So if we look at the diurnal cycle of convection, we have something like this, where that was that stable boundary layer, and then as the sun comes up, we have this strong growth through that as we go to something at this time of day will be this nice dry adiabat over land. And of course, this will be much stronger over land compared to ocean due to the surface heating. Okay, so as I mentioned, if we go back to these profiles, during the day as that layer deepens, if we go deep enough, it depends on our relative humidity near the surface, but if we go deep enough, eventually we can form clouds through condensation when the relative humidity basically reaches 100%. So Simona already talked about the fact that then, of course, we go from a dry adiabatic lapse rate to something which the temperature falls off more slowly in height because we have the moist adiabatic lapse rate that Simona basically introduced. So I just put this in to remind ourselves, but I didn't go into details because I knew she was covering this in her lecture. Okay. And the point at which the saturation occurs, remember, Simona referred to this as the lifting condensation level. So this is just to link in with her lecture. Okay, as we lift that parcel, okay, we do need to decide, when we have this hypothetical ascent, what then happens to that condensed water. Okay, so we form cloud droplets, but those cloud droplets can then eventually also basically bump into each other, form larger droplets, and eventually form droplets that can precipitate out, okay? And it's a very non-linear process, okay? And any of you that have ever had a shower with, not a shower curtain, but with the hard perspex glass, there's like an echo at a certain point here, like a harmonic around the room. So if you have a shower, the glass, you've seen this rainfall process happening on your glass, where first of all you get condensation of very small drops and they stick to the perspex, and eventually one will be slightly larger and will start to move slowly, and then it will bump into other droplets, and then all of a sudden, boom, it moves down very quickly. That is rainfall production. Warm rain process is happening in your shower, okay? So another kind of experiment that you can follow. So when we lift our parcel, we have to decide, do we reach the threshold of drop size distribution so that we can form rain and it drops out? Or does the water stay inside the cloud? And that really depends on basically the depth of the cloud. So shallow convection, we'll see, generally doesn't precipitate. It can do, form drizzle. Whereas with deep convection, the vast majority of the condensed water actually falls out as precipitation. And I'll come back to that as I go on. So I said I'm going to go through different heights of convection. So we've talked about the dry, well-mixed layer. Okay. If we form condensation, we can form basically a type of convection known as stratocumulus cloud. Okay. Now, stratocumulus cloud, we've got a cartoon here. Okay. So we can see it's a turbulent mixing layer. We've got convection going on. We've got condensation at the top of this cloud layer. Okay. We can have formation of drizzle. Okay, but usually stratocumulus is not precipitating at the surface. It's non-precipitating cloud. Okay, and this turbulence is driven by two processes fundamentally. We can have surface fluxes, okay, heating from below, but we also have turbulence driven by cooling at the cloud top. Why do we have cooling? Because basically we have long wave emission of radiation of photons to space from the cloud top. Remember, clouds in the infrared basically are like black bodies, okay? They emit to space, sigma t to the fourth, okay? Out towards space, so we have strong cooling at the top. Cooling means a buoyancy perturbation. We have a buoyancy flux and air that's sinking, mixing into this layer, okay? So stratocumulus is canonically defined as a well-mixed, radiatively driven, and it's usually non-precipitating thermal boundary, okay? So here we have, for example, the heating rate we can see with a strong negative peak at the cloud top associated with this emission to space, which is driving the turbulence within this boundary layer. Okay. So here I've taken up a plot from Bjorn Stevens showing what the profiles should look like through this layer. So we can see on the left here, this is our theta profile, and we can see this very strong inversion at the boundary layer top. Okay, and if we look at the humidity, this is the total water. So this is water vapor plus the liquid condensation added together. We can see that in the layer, it's approximately constant, and then we have that strong dry drop-off at the cloud top. Okay, so question, we have a cloudy layer here. This is the total water, which is the vapor, specific humidity, plus the liquid water, the specific liquid water. What will those individual profiles look like? So the humidity, let's imagine the humidity in the subcloud layer, this total water, because the QL is just 0, so this is just the humidity, it's going to be constant. Okay. What about in this layer? What's going to be happening to the vapor and the liquid water? What do you see? What will happen, first of all, to the water-vapor mixing ratio, or the water-vapor, the specific humidity? Will it be increasing, constant, or decreasing? Decreasing, very good, because we're forming clouds, okay? And so if we look at the individual profiles, I've kind of sketched them on the top. Our water vapor will be going down, and the liquid water will be going from 0 and then increasing. Okay. If we don't form precipitation, because we can assume, to 0 order, we assume that cloud droplets are so small that their terminal velocities are also very small, and we can assume them to be 0. In other words, cloud water droplets are just carried with the flow inside the Andes. Okay? We assume that they don't move relative to the air that's carrying them. Okay? And so if we don't have precipitation, they just act almost like a tracer. Okay? And so we refer to this, because the total of the water vapor plus the liquid water is basically constant, we often refer to this as the adiabatic value of the liquid water. You can say the adiabatic liquid water content or the adiabatic liquid water mixing ratio, okay? Because we don't have any loss due to precipitation making droplets fall relative to the flow into the subcloud layer where they can evaporate or even reach the surface, okay? So in this case, we have the adiabatic liquid water content. I did mention stratocumulus can drizzle. We can't go into the details in a 1-hour lecture, but I just wanted to show this picture where it's still active research, but we fundamentally believe now that in the modeling of these kind of clouds, that if you have precipitation processes, and there's also a role for cloud top entrainment, then you can actually break up these closed cells into open cell, basically stratocumulus. Okay, so part of this open cell structure is because we basically have precipitation formation in this layer, which reduces then the liquid water below the adiabatic value. Okay. So I said I wanted to kind of move across this diagram. So I want to now look about going towards now from the stratocumulus to the kind of the trade cumulus here, where it's basically, should we say, a cloud type that usually has a much, much lower cloud fraction. We saw the stratocumulus in the cloud cell. It has a very high cloud fraction, okay? I put all three up here. I'm always fascinated by schematics. So when I tried to give the talk on the cyclones last week, and I was amazed there. It's just like, you could find literally tens, if not hundreds of like different cartoons of cyclones. So even here, I just for a bit of fun, I thought it would kind of going through time from David Randall's 1980 schematic of this overturning circulation through 2005, we're getting a little bit. This is now Sandrine's cartoon from 2015, showing this overturning circulation. Fundamentally, though, they all have these elements of a lower inversion over the coldest sea surface temperatures, a raising inversion height as we move towards the trades, and then we go into the deep convection happening over the warmest waters. And we want to explain why that is in the latter parts of this lecture. Okay. So part of the fundamental thing is as we go to this turbulent layer inside the stratocumulus, as we move towards basically a deeper layer, the trade cumulus fundamentally is also associated with a decoupling of this turbulence. So then we actually have basically a well-mixed boundary layer, but we have a decoupling of the turbulence of the cloud top mixing and also the boundary layer. And there are actually several different mechanisms that can cause decoupling of this turbulence. Basically, it can be a reduction of the intensity of the radiative driven circulation or a stabilizing of the subcloud layer. And so basically, the processes that can lead to this are, for example, if we have shortwave radiative heating in the subcloud layer, so if we start to have breakup through, for example, precipitation, lower cloud fractions, we can start to have shortwave heating of the layer below. We can have, and then as we move towards warmer SSTs, this is absolutely fundamental that as we deepen the layer, we have more entrainment into the layer, which deepens the mixed layer to such an extent that we're bringing drier and drier air into that layer, and we're reducing the humidity such that we can't basically sustain the mixing right through that deeper layer. Okay, and we can also change the stratification in the subcloud layer by precipitation evaporation. So even if it's not raining at the surface, if we have drizzle formation starting as we deepen the layer, okay, so we have a deeper layer, larger droplet sizes due to that deeper layer because the adiabatic water content is getting larger as we move up, we can start to have drizzle formation, which can then cool the subcloud layer. Okay. And so again, here's a cartoon to kind of illustrate trade cumulus profiles. And we can see now that we have this subcloud layer, which is very well mixed in the total water, but now we have a gradient in the total water through this trade cumulus layer because now we have precipitation occurring that's removing, and we also have stronger entrainment at the cloud top. Okay, so that produces a gradient here. We can see the theta, again, well mixed, okay, and then we have an increase in the layer of the trade cumulus going towards this trade inversion. The liquid water content also increasing through this layer, But notice this dotted line is showing the adiabatic value. So remember, the adiabatic value is what we expect if we lift a parcel of air conserving all of its water. So if it condenses, it stays in the parcel. And now we're below that because of the precipitation processes, okay? So I've put basically a couple of kind of general observations. So we can see this nice picture here of a kind of a trade cumulus boundary layer. I'm sure you've all seen these kind of examples, either looking at satellite data or looking out of an aeroplane window. I don't know if you're like me, whenever I fly, the person sitting next to me always thinks it's my first ever flight. Because I'm always there with the smartphone out of the window, this kind of thing. And they would say, oh, first flight for you? I said, well, yeah, maybe. It's too embarrassing to admit that you're addicted to photographing clouds. Anyway, I shall move on. When we look at shallow cloud systems, and again, I mean, we could have a whole lecture just on shallow cloud organization. I'm just putting one picture in here to give you an example. This is from Sunscreen Boney at the top. These are shallow cloud anvils where the air is meeting that kind of trade inversion and it's spreading out at about a kind of 3-4 kilometer height in the atmosphere. But we can have a variety of different organization types. So some of you might be aware of this literature that started looking at the organizational types where they've been divided up into categories of like fish, flowers, sugar, and gravel. So I've just taken this. I was a little bit lazy. It's just from a paper that one of my postdocs is working on now at this organization. You can see these very different structures of the cloud in the boundary layer. This is using GO6 Channel 2 visible imagery in the Caribbean area. Okay. So one thing I do want to quickly point out here, if you look very closely, later in this lecture, I'm going to start to talk about cold pools, which is air, which is negatively buoyant, that kind of drops down to the boundary layer and spreads out. Even in these shallow convection systems, you might be saying, okay, these are the flowers. Look what we see here. Okay. These are already evidence of cold pools. I'm going to come back to this later when we look about deep convection. So this is air that's spreading out, and on its fringes is lifting up air mechanically and bringing it to saturation. Okay. Okay. So when the air meets this inversion, okay, mostly we see that as we, like, especially when we had that dry layer, we had that very strong inversion. The parcels, when they overshoot, are much colder than the environment, and ultimately they just sink back down into the boundary layer. Okay. As we go to warmer and warmer or higher moist static energy surfaces, then we get to a situation where that inversion is getting weaker and weaker. Okay, and I'm going to show that overturning circulation again. So then we can start to get to situations that look more like this. Okay. So again, I just took this last week, just as an example. Okay, this is basically in the Western Pacific warm pool region. It's an atoll radiosonde, so it's an area that's surrounded by ocean. Okay, and if you look very carefully, you might need to get your opera binocular glasses out. But if you look very carefully near the surface, again, remember these green lines are lines of constant theta, and we can see that we lie parallel to one of these lines. So we have a well-mixed boundary layer, but we don't have this big, strong inversion anymore, okay, because we're over much warmer surfaces, okay? And basically, if we lift a parcel of air, this is our humidity, which you can see it's well-mixed. It lies parallel to one of these lines. We actually reach this point here. And very helpfully, this website actually plot this grey line, which is a hypothetical parcel ascent. We can see it as we lift this parcel. We reach saturation at this point, and then we start to follow a moist adiabat, which was that adjusted line which accounts for the phase change of water. Okay. So we can see that in some cases, if we lift a parcel, and we're going to talk about this in a moment, this parcel, you have to look very closely. I should zoom this out. But if you notice, it's slightly colder than its environment, so it's negatively buoyant. Let's imagine we have enough momentum that we actually reach this point. Now we start to become warmer than the environment. And so now we have a positive buoyancy and the air is going to be accelerating upwards. Okay? So let's just imagine for the moment that for some reason we have enough energy in the parcel, either just through momentum or it's being mechanically lifted, that we can get to this point. It's just going to carry on accelerating all the way up to here. Okay? And so this means that in this case, we would have parcels of air going well in deep convection. We refer this to going all the way to the upper troposphere, okay? So in these deep convective events, we've got a number of things we need to consider. And then basically we need to know about the properties of the air in the updrafts. But we might also want to consider, for example, the process of the mixing, because these clouds are very turbulent between the cloud and its environment. And then, of course, we can also have evaporation of basically cloudy air, and that cooling and the drag can lead to then downdrafts. And then we have the precipitation processes, okay? We might consider. So in terms of this deep convection evolution, we can see that we have basically a formation stage, the mature stage where we start to have then basically formation of downdrafts, and then we have the dissipation stage, okay? So in the cumulus stage, basically it's like similar to non-precipitating. This looks like a fair weather cumulus. You've all seen days where you start to see these kind of clouds, you think, uh-oh, is it going to rain later on? And often, if these parcels are not quite energetic, it was like that yesterday. I saw around this kind of cloud, but there was no deep convection in the vicinity of Mexico City. A little bit more energy, you can get through that kind of negative layer, and then maybe these things carry on up, and basically we get this kind of cloud basically form, the mature convection, okay? So, and then we have basically, as I said, we can have changes in buoyancy due to basically evaporation of precipitation, leading to downdrafts, and eventually we get this dissipating stage where the updraft is just dying out, the downdrafts also decay, and we're just left with this anvil shield. Okay. Lifetimes, we can estimate on the back of the envelope what this might be. It's basically if we take the depth of the troposphere, okay, let's just say 10 kilometers for ease, okay. So in the tropics, of course, these things can go up to 14, 15 kilometers. Just say order of magnitude, 10,000 meters, divided by typical updraft speed, which might be 5 to 10 meters per second. So if we say 10 meters per second, we get 1,000 seconds. Okay, 5 meters per second, 2,000 seconds. Gives us a kind of an order of magnitude lifetime of like 20 to 40 minutes, okay? So the whole thing has a lifetime of roughly half an hour to an hour for one of these cells, okay? I'm not going to get time to talk too much about clustering, but just to mention that we have a tendency for these things to cluster. Convection can beget convection for a variety of reasons, both through cold pools, which I will talk about, but also radiative cloud feedbacks, which I won't talk about, okay? If you remember, the saturation vapor pressure or mixing ratio is a very nonlinear function, okay, and temperature's dropping off with height. So let's imagine in the tropics, maybe our surface temperature is around 25 degrees Celsius, okay? So we're looking at something like, 290, 300 Kelvin at the surface in the tropics, okay? So 27 degrees, 300 Kelvin. Upper troposphere temperatures, okay, if we're getting all the way up to the tropopause, we're talking about 190, 200 Kelvin. So that's a huge change in temperature, okay? So that saturation value is coming down to basically something close to zero. So this is why, in terms of most of that water then won't be carried inside the cloud, but will drop out as precipitation. Okay, so we have very high, what we call precipitation efficiencies. Most of the water near the boundary layer in these clouds will actually fall out as rain. Okay, whereas with shallow convection, because the temperature difference is much smaller, even if we're producing precipitation, we'll still be leaving a lot of that water near the surface inside the cloud in the form of water droplets or ice if we get above the freezing level. So, up to the freezing level for that kind of mid-level convection, the congestors. Okay, this I can kind of skip over. I wanted to leave it in here for reference, but Simone has already talked about the fact that we have, this is our dry adiabat, this is our moist, and so we have these different, should we say, regimes of conditionally unstable. If we have a profile of temperature that lies in between, then the stability depends on the properties of the parcel, because if it's subsaturated, we lift air, it's going to be colder than the environment and will sink back down. But if it's saturated, it's going to be warmer and will carry on up. So the stability depends on the properties of the parcel. The reason why I wanted to leave that in is because we want to now start talking about parameters. Now I've zoomed in on that boundary layer. Remember that parcel that was colder than its environment? So here we have an inversion. This is our lifting condensation level. We conserve water vapor, we conserve temperature. Then we're going up a moist adiabat. We're colder than the environment, okay? And this is our level of free convection where we become warmer than our environment, okay? So when Simona talked about finite amplitude instability, let's imagine a parcel which is somehow mechanically lifted, but I only lift it to here, and then I let it go. What's going to happen? It's going to drop back down, okay? Instead, if I can give it a finite perturbation, I'm lifting it over an object, and it gets lifted mechanically all the way up to here, or it has enough momentum to get up to here, then basically it's going to carry on upwards, okay? So small perturbations, stable, larger perturbations, unstable, okay? So that refers to what Simona was referring to when she talked about finite amplitude perturbations. This area here on these graphs, areas are proportional to energy. This is the energy we have to overcome, either through momentum or from mechanical lifting to bring us to this level. So this area contained by the parcel and the environment is a negative area of energy that we have to supply to the parcel in order for free convection to occur, okay? So we can define an energy, if our parcel goes all the way up to the top, we have two energies that we can define. And those energies are simply the integral of the buoyancy over the parcel, okay? So the cape is the energy that's available to the parcel all the way through to its final destination at the level of neutral buoyancy, including this little part of the sin, starting from the initial level. And the sin is just the integral of the buoyancy over this part here, okay? So this is the available energy to the parcel. So it's referred to as the convective available potential energy. Okay, so we have sin and cape are the two energies that are relevant, and then we have the lifting condensation level, the level of free convection, and the level of neutral buoyancy, where the air, again, basically at the tropopause in the parcel equals that of the environment again. Okay, so again, this is another profile, and you can see, in fact, they give the cape value here. It's basically 1,500 joules per kilogram. Okay. They also, by the way, give the sin, but for reasons I probably won't go into in this lecture, there's a bit of a glitch in the calculation in terms of if there are several points where it overshoots and goes cold, it only counts the very first one. So you have to be careful on their website for the sin values. They're not always very reliable. Okay. So triggering, I said, somehow we have to get over this sin. Okay. And there are lots of different ways that this can happen. We can have forced descent over orography. So there's a little cartoon here from a 1970s paper that talks about different ways that air can be lifted, okay? We can have air lifted mechanically over colder, denser masses, for example, at fronts. So in mid-latitudes, cold fronts, which are quite steep, can have convection embedded in them because of the lifting of the air. Altocumulus is mid-level convection through layer instability, where we lift an air mass, a layer, and it becomes unstable because its theta E, its equivalent potential temperature, is falling with height. I don't have time to introduce that here today, but just to kind of mention it. Or we can have air that's forced to be lifted over these cold poles. Remember that cold pool structure? I'm going to show you in a moment, okay? So the air reaches these, is lifted over the, basically the spreading cold pole. We can have surface convergence due to low pressure perturbations, land sea breezes. Elevated heat loads. Here's an example. I took this snapshot several years ago. I live here. This is a radar. So this is not forced descent. The large-scale synoptic situation didn't have any convergence. There was no front coming through. But basically, this is convection over the high terrain. You can see the speckled mountains simply because the air in vicinity of the mountain tops is heated. So you have basically a heat low of the air over the mountains because it's warmer and less dense than the air away from the mountain at that level, and it drives convergence towards the mountain top. Okay, so that's why you can get thunderstorm initiation over high terrain, even without any large-scale synoptic patterns. Okay, you can have triggering through surface warming in the diurnal cycle. So this parcel lifted here basically would follow this adiabat, and we have sin, but if we warm enough, eventually we can see that without changing the humidity, so we're over land, perhaps we have a small latent heat flux, eventually we no longer have sin if we reach this temperature in the diurnal heating, okay? So operational forecasters in Africa, because convection prediction in weather forecast models is still not that reliable, my colleagues I've talked to, they still use this as a back of the envelope to try and see how much they trust what's going on in the forecast for situations where they don't have any large-scale synoptic situations causing convection, like African easterly waves, just to see if they expect diurnal convection triggering in the afternoon. I love this photo. I need to just show it, just to show you these beautiful flat anvil tops. This is our level of neutral buoyancy. Okay, beautiful flat tops. Where are the updrafts? It's like that thing we have to spot. Where's Hubert? Where are the updrafts? Here they are. So you can see the air overshooting, and then it's sinking back down. We have this turbulent nature of the cloud here because of the overshooting. And then eventually, you know, these gravity waves will start to dissipate, and we have a very flat top, okay? So what else do we see here? Lifting around the edges of these cold poles, triggering new events. Convection begets convection. Quick couple of slides. I noticed I was really worried about overrunning. I think I'm going to be tight, so I'm going to skip through these really quickly. After the Second World War, we started to equip aircraft to look inside clouds, to get a view for the first time of the nature of clouds, really. And so these instrumentations had a fast enough response time to start to reveal pictures like this, where flying through the cloud at 100 meters per second, so if you have a response time of your instrument of 1 second, you get about 100-meter resolution. The temperature instruments are actually quite a bit better than that, so they could get resolutions of just tens of meters. And if we look at the liquid water profile, for example, here in the middle, look, very small oscillations, okay? Edges of the clouds, lower values, and big oscillations. What's going on here? This is actually very close to the adiabatic value. So in the middle of the cloud, we've got air that's lifted from the surface. This is quite low in the cloud as it's developing. We haven't had precipitation reducing the value, and it's not mixed. On the edges, the turbulent natures bring in dry air in. It's evaporating these water droplets. And it's also, therefore, the evaporation driving negative buoyancy perturbations. Remember, the buoyancy is related to the vertical temperature, and then also downdrafts. Look at the vertical velocity. Updrafts in the center of the cloud, downdrafts on the edges, and very turbulent. Those eddies mixing in at the edge of the clouds, strong mixing at the edges. In the interest of time, I'm going to kind of skip over this. It's really, I'm going to leave it in for reference. It just talks about the fact that humidity, specific humidity, is linearly mixing. So if we mix a mass M1 from the cloud and M2 from the environment, we can just do a linear combination of the two, and that gives us a specific humidity. And if we make some assumptions where we ignore the heat capacity of the vapor and the liquid, or just take the heating capacity of the dry air, temperature is also approximately linearly mixing, which actually means that on this kind of like, for example, on the vapor pressure curve, we can say that we can just draw a linear mixing line between 2 points. Actually, I should have put a specific humidity curve here, not saturation. So we can take subsaturated air and subsaturated air in different masses. And if we take equal masses, we'll actually have a resultant parcel that lies right in the middle of these 2 points. Okay, but if we take like 3/4 and 1/4, then we can end up here. So it'll always be on this kind of linear mixing line. And you can see that these 2 subsaturated parcels, if we mix them in these proportions, we'll actually have a saturated parcel that results. Okay, which is why, for example, in Europe in the winter, you can sometimes in moist environments see your breath when you're breathing out because your saturated warm air is mixing with the cold subsaturated air and producing a saturated resulting parcel. Okay, I'm going to skip over this slide because I'm a little bit late and I'm worried about this, but it's just about the episodic mixing. Mixing, of course, means that this is our kind of hypothetical parcel ascent, but if we're mixing air from the environment, which is both cooler than the parcel and also drier, it's going to be moving this air mass in the parcel towards the environmental profile. Okay, so if we have mixing in the updrafts, it's going to be changing the level of neutral buoyancy and reducing the cloud top height. Okay, so I don't have time to talk about parameterization today, but one of the kind of paradoxes in the late 60s, early 70s was why, when we look at the level of neutral buoyancy, it seemed to coincide with what we expect from an undilute parcel ascent. Okay, But we knew that there was mixing going on in clouds, as we saw from the aircraft observations. Okay, and so it kind of pointed to the fact that a lot of the parameterization schemes that just take a bulk mass and assume mixing right through that bulk mass as the cloud goes up really misrepresent that process, because we've got to consider a cloud to be part undilute to reach that level of neutral buoyancy, but also part mixed, because we have basically air leaving the cloud all the way through the troposphere during its ascent, which kind of is what I was trying to show here, but in terms of this episodic mixing. Okay. I want to do a couple of minutes on downdrafts from clouds, and then I'm almost finished. If I get time, I'll put in a slide on quasi-equilibrium as well. So I mentioned the fact that we have precipitation which can evaporate in the subcloud layer, okay, and that's not just the lowest couple of kilometers if we have strong wind shear, because if we have shear that shears over the cloud, we can actually get precipitation evaporation through a much deeper layer. So the amount of cooling depends also on the shear, which we don't consider very much. Most parameterization schemes and models don't account for wind shear in their kind of calculations of convective mass flux and heating and evaporation. And also the drag of precipitation means that we have then basically resulting cool air, which is dense, which is falling and then spreading out in the form of a downdraft at the surface. Okay, so here we have these gust fronts. And remember the mechanical lifting of the air, because we have less dense air, more dense air, so the less dense air wants to rise over these fronts, it's lifted, can then trigger new convection, which is what we saw on that satellite picture. Here's another example, which is even more, should we say, emphasizing this. Mature deep convection cloud, spreading of cold poles. What do we see inside the cold pole? We have inhibition of any kind of shallow cloud. It's completely clear because the air is dry and it's dense. Okay. On the edges, though, we get these beautiful line structures where the air is being lifted and it's forming this kind of arcus kind of cloud on those fronts. And sometimes that lifted air can then be just lifted through that kind of thin layer and reach the level of free convection, especially if we have collisions. See that new one just starting there between two cold poles, which provides that extra little boost. Okay. So that we have new convection starting, okay? And this will happen in just the right amounts to keep us, as we'll see later, to a kind of a smallish value of Cape. Okay. So these are, again, other examples of cold poles. This is actually a very old simulation I did like 25 years ago with a kind of a 300-meter resolution. It's only 100 by 100 kilometers. Just showing cold poles in a cloud resolving model looking down from the top. These are just basically temperature perturbations. And you can see these cold poles spreading out very quickly. And if you look closely, you can see the new events starting on the edges of very mature cold poles. And that was actually due to a thermodynamic role of the cold poles as well in terms of their moist static energy perturbations. But, okay, so we have triggering. The triggering of new convection, I said about the lifting, if we have background wind shear, can actually be preferential in one direction because we have vorticity associated with wind shear. And we also have vorticity of the wake front because we have the air spreading out and then recirculating at the wake front. Okay. So in this direction, you can see that the vorticity of the shear and the vorticity of the wake front are actually in the same direction. And that kind of doesn't really, it's not very conducive for lifting the air vertically because the air masses are really sheared over in this enhanced vorticity. In this direction, instead, you can see the vorticity of the wake front and the vorticity of the background flow are basically in opposite directions, which gives you more upright lifting and can lift you through. So in those cases, if you have appreciable shear, you can actually get then linear structures forming, such as squall lines. I don't have much time to talk about organization of convection in this lecture, in fact, no time at all, but I wanted to mention this as an example again. And again, this is an example right near where I live of one of these squall lines which was triggered and is actually propagating southward, okay? So again, not just radio sondes, but if you have a chance, if you have a radar nearby and you can look at it, go to the Windy app or the Windy website, they have the radar information there. Again, I encourage you in the rainy season, take a couple of minutes over your coffee break and have a look at these radar sequences because you really learn a lot from experience of just surfing these things. So lastly, I just wanted to have 3 slides, and I'm going to finish off on what sets this tropospheric temperature profile. No? So if you look here, for example, again, this is another profile in the deep tropics where we have the temperature very close to this moist adiabat. So these blue lines here are these lines of constant theta E that Simona introduced. Okay, and note, by the way, we don't have time to talk about this, but the very interesting structures in terms of the humidity in the vertical. Okay. So basically what sets that, so this is going to kind of lead into some of the other lectures. I'm going to do this very briefly. If you just simply do a calculation of the radiative equilibrium, okay, so you can do this very simply if you assume a black body atmosphere, but to make things simple, even just on an analytical way. So basically, if you do just a radiative equilibrium, so we just assume that we don't allow the atmosphere to move at all. Okay, we just freeze all molecules in place for the moment. Okay, you get a profile that looks like this. Okay, so in the stratosphere, it kind of looks okay to what we observe, because in the stratosphere we have a radiative equilibrium. Okay, but in the troposphere, it's drastically off. We end up with a surface temperature that's way, way too hot, and the upper troposphere temperatures are way, way too cold. And that's because a radiative equilibrium profile is not what we see, because, of course, this is massively super adiabatic. Okay, so if we were then to start off with a profile like this, let's imagine if we took a weather model, like the ESMWF model, and we initialized it with a profile like this, and then we let it go, chaos would ensue. We would have tropical cyclones, everything. The whole thing would just go crazy in terms of convection everywhere. Why? Because this is unstable. So this air will rise like crazy, and this will sink, bringing it back towards, as I said, a profile of moist neutrality. So this is our dry adiabatic lapse rate, and this is our moist adiabatic lapse rate, which is much closer to what we observe. And again, it's because the atmosphere is essentially invisible. So this was the work that was referred to by Simona, by Manabi and Strickler, that first basically showed this. Basically, this concept of radiative convective equilibrium giving us our kind of a mean profile in the troposphere. Okay. So what that means is situations of what we can perhaps call triggered convection, where we have large amounts of CAPE, are actually quite rare. So examples can happen. So for example, in the American Midwest, where they have basically the twisters occurring, basically very vigorous convection. That happens because you have 2 different airflows of very dry air from the desert region over the moist air from the Gulf. And that dry air causes you to have a large amount of SIN, capping convection, that allows instability to build up above. Okay? But situations like this are actually quite rare, where you have a lot of CAPE in the atmosphere that then is released in explosive convection. Okay? So a lot of the work on cyclones in the 60s, which was based around the idea of CISC, was really based about the idea of converting CAPE in the atmosphere into motions. Okay? And that's not really how things work, because most of the time you don't have very strong amounts of SIN blocking off CAPE. Okay? What you normally have is a situation of basically quasi-equilibrium, where your consumption of CAPE by convection basically balances to a good degree its generation by the large scale. Okay? So we can assume that basically we have small amounts of SIN, and that convection is in a statistical equilibrium with the forces of radiative cooling that's acting to destabilize. But I think, Spencer, you'll be talking more about this now in your lecture. So as I'm out of time, I should really kind of move over this. So I had a slide here that talks a little bit about this, quasi-equilibrium, where you can imagine, this is from the original paper, but you can imagine this as change of CAPE over time, and this is the forcing due to surface heating and cooling, and the change of CAPE is very small compared to the forcing. Okay, so that's basically saying that convection is very, very efficient at removing CAPE that's generated by large-scale processes. Okay. As a result, the consequence of that is basically the temperature of the free troposphere is basically set by the subcloud entropy. You have a kind of a one-to-one relationship. So basically, if you warm the the boundary layer, you increase the moist static energy, okay, then you have an adjustment of the free tropospheric temperature. So essentially, when we look at a map of precipitation, this is like spring precipitation, where this deep convection precipitation is occurring is where you're associated with the highest moist static energy in the boundary layer. Okay, this is just to kind of lead into what Spencer's going to be talking about in some of his lectures later on. Okay, so the convection is linked to the moist static energy of the boundary layer. Okay. So if we go back, and I'm just going to finish off here, I'm going to skip over this because I don't have time to talk about waves. That's going to be coming up in another lecture. I just wanted to put a pointer. But if we actually look at this cartoon then, these are the warmest sea surface temperatures. If we look at the Walker circulation, this area here is where we're going to have the highest moist static energy in the boundary layer. So the air that's moving up is following a moist adiabat here. The air then, basically, this warming is spread out by gravity waves over the tropics. So in the free troposphere, the air temperature is not changing by more than a degree or so due to the very efficient propagation of gravity waves. So the temperatures here are almost the same as they are here. Okay. But the surface of the ocean is much cooler. So this is why in these areas you have a much stronger inversion at the top of the boundary layer, because the air here has the properties set by the deep convection over the highest moist static energy, okay, and the air in the boundary layer in the theta is set essentially by the ocean below it, okay. So you have strong inversions, weakening and deepening as you move to higher temperatures, and then you have the deep convection region over the area where you have the highest moist static energy. Okay, I'm actually 5 minutes over, so I'm going to have to stop, and I will stop there.
Any question? I guess we got time for 1 or 2 questions.
Okay. Oscillation, Kelvin waves, and so on, but that's for another lecture. Yeah. Okay, I'll hand over to Dave. I strangle myself.
This looks dangerous. So she has to put up my. Am I doing this right? What's that? Oh, around like that? Oh, 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 whoa. That's too loud. Is that okay? What's that? I can't speak Spanish. Okay, so I didn't realize. I do have a loud voice. I know that. Maybe if I put it down here. Okay. Well, I didn't realize that actually. You want me to use that one, Alejandro? Oh, that's my. Oh. Oh, right. Yeah. Well, yeah. Pues no sé. ¿Sí? ¿Está bien? Ok. Bueno, vamos a cambiar a español, ¿no? ¿Está bien? No se ven muy entusiasmados. Ok, bueno. Okay. So anyways, yes, I didn't realize that actually, Adrian and I were twins. The presentation that he gave you was basically my kind of career into convection and atmospheric sciences. Although I've become much more observational in the last 15 or so years, something like that. But anyways, we changed the schedule around a little bit after talking with Adrian and Simona. They wanted me to do something a little more qualitative, actually using real, so to speak, real world data and talk about convection, what we actually observe. And so that's kind of how I'll base my talk here. It's very qualitative, lots of figures, and actually a lot of the things that Adrian mentioned. Yes, look at radiosondes. I have some of these kind of results. I use a lot of satellite data, the GOES data. And so I'll show you the results, and I'll give you the bigger context of why I do what I do and what I'm doing with respect to the talk of Spencer, Alejandro, Simona. Okay, so you guys can, and well, Christian, yeah, I think you and I are more, maybe aligned a little bit more. Okay, so I don't know, how do we do this? Oh, I have a way to, I can change it? Wow. You can tell I don't get out much, right? Okay. So anyway, so here's my idea. We were just looking, for example, think of what Adrian was just talking about, how over the ocean this happens and that happens, and I'm sure actually Spencer will talk something similar. I'm sure Alejandro will talk something similar. But when we actually consider topography, we're going to find out that convection and its behavior varies radically. Okay, doesn't mean that convection is the phenomenon that Adrian was just talking about is different, but we'll find that its behavior, its intensity, its organizations, its lifetimes are very different, relatively speaking, to what we see over the oceans, particularly the tropics. Okay, and one of the motivations, and also like actually how your configuration of your continental areas are with respect to the ocean is going to be important too. And like I said, if you look at theories, and when I say theory, I mean I'm speaking in a very general term. Theory concepts of how convection relates to large-scale atmospheric conditions, which is kind of the last part that Adrian was talking about in his talk. All of these have basically been developed over the ocean, or they assume ocean surface temperatures. Okay, that's very different than over land. Okay, and I'm going to give two regions. That's because basically most of my work I've done in the Amazon and in the North American monsoon region. Okay, so that's the context for this. Okay, now my motivations. Okay, why do I do what I do? Okay, first I have my scientific questions, how I approach it, and what kind of the goals are, so to speak. Okay, so something I'm interested in. What are kind of the what we call large scale, and I'll define more or less what I mean by large scale and small scale, convective scale. How does it help determine the intensity and frequency, for example, of deep convection? And why and how do these conditions vary geographically? And again, I use remote sensing, like the GOES infrared images, basically cloud top temperature, GPS met, and I'll talk about this in detail on my next talk, more detail on Wednesday. Okay. I use a lot of lightning data. Lightning is only associated with deep convection. You don't get lightning in any other condition, so it's a nice variable to use. I don't personally work with models, but I work with a lot of people that work with models. Okay, and I'll give you a context there. And as Adrian said, radiosondes. I've downloaded billions of gigas from that website. He's talking about the University of Wyoming. Actually, you can tell the guy, I forget what his name is, hey, will you organize everything for me and send it to me from the station in Mexico City? I've done that before, and he'll give you 10 years. Just, he'll do it for you. I think he still does it. I don't remember what his name was. But, and also eddy covariance flux towers. I'm not sure if you're real familiar with that ideas, but it's also related to like the turbulent boundary layer that Adrian was mentioning, talking about. Okay. What are my kind of goals? Create metrics, or that is values that you can use to compare with real world data. Okay, and I do that to what I say challenge models, and also to actually provide data from them, and also to assess, test theory relating convection at the large and convective scales. Okay, If you want to make friends and have people love you and listen to you and invite you, don't do what I do. Okay? All right. So what's a fundamental issue? Now, this is over the Amazon region. Like I said, it's one of the regions I'm going to talk about. How does deep precipitating convection relate to a large-scale environment? Okay. Now, basically, again, the scales are not exactly identified, but when you're in the atmospheric sciences or any type of physical environmental science, scales, time and space, are critical. You have to define these. For example, they talked several times about scale heights in the atmosphere, the scale height of the atmosphere, the scale height of water vapor. They give you just a baseline to look at. Okay. So the convective clouds typically grow on the scale of hundreds of meters. Okay, that's at the kind of baseline where the turbulent flux is up into the atmosphere. Okay, then they can grow and grow, and on the larger end, they can reach about 1,000 kilometers, which is pretty large. Take a look here at these long lines from the northeast coast of Brazil to Colombia is about 2,000 kilometers or so, maybe a little bit more. So look at how long these lines of convections are. That's pretty damn huge, right? Take a look at these little baby cumulus clouds. You might want to ask yourself, how does it go from this to that, all in a period of one day? That seems pretty strange, no? Okay. So the thing is, well, only certain conditions will allow that to happen. Okay, obviously over the Amazon and over the deep tropics, it's much more common. Okay, less common here in Mexico City. Okay. And again, like I said, most of the theories, when you talk about convection and larger scale interactions or larger scale conditions, have focused on the ocean. And you might say to me, well, why? Well, because the ocean is much more homogeneous, right, compared to land. And that makes theories simpler and easier to work with. Okay, it's not a criticism, but that's just reality. And also, most of the tropics is ocean. Okay. However, as far as I know, I'm not real sure about this, most human beings live on continents. Okay. So also in Adrian, I was citing one of Adrian's paper. I don't know why I didn't. But also when you use idealized models, and that could actually be like a conceptual model, but also like an experimental model with numerical, where you represent physical process numerically, and the interactions, including parameterizations. Okay. Now, in terms of the actual convection, if you're over a continental region, damn it, sorry. Right, this is very scary. What am I doing wrong? Go back, please. Okay. Okay. So if you're over a continent, the actual nature of the topography, or even the vegetation, or whether you're at the edge of the continent and by an ocean, that can actually have a great influence on the behavior of the convection, its intensity, its lifetimes, etc. Okay, and that's okay. There's something wrong here that didn't show up. I have a whole nother bunch of lines here. Algo está pasando raro. Well, anyways, okay, I mentioned, it's not appearing here, but there were several very large scale, or I shouldn't say large scale, huge in terms of money experiments. One was the LBA. There was also NAME. That was LBA was in the Amazon. NAME was in northwestern Mexico. That was 2006. There's also Relámpago. And that was in, I think, 2016, 17, I'm forgetting. And that was in Argentina. And they also did the Go Amazon, which was a really huge project in 2014, 15 in the central Amazon. Okay, and that one of the goals of all of those experiments was to actually understand how does the landscape, topography, et cetera, urban areas, things like that affect the intensity of the convection. Come on, what? Bueno, creo que es nada más estos dos. Entonces no creo que haya problema. Sí, está bien así, ¿no? Eso sí está bien. Okay. Okay, so, all right, hope you're following me so far. Okay, so, for example, and I'll talk more about this on my talk on Wednesday morning. Okay, I'm not going to go into the details here, but I'll go a little more into why some of the specifics of, like, for example, self-organized criticality, thermodynamic control, and they're basically try to relate a large-scale variable, in particular column or precipitable water vapor, with the nature of convective activity. Okay, but over a long period of time, like I said, even observational studies, not necessarily theoretical ideas and stuff like that, they have focused on the relationship between the amount of water vapor in the atmosphere and the precipitation, and what is typically revealed is a very nonlinear relationship, very strong nonlinear. As the water vapor amount increases in the tropical atmosphere, the intensity of the precipitation tends to decrease, kind of baseline like that. And because of that reason, other theories have kind of come about. But like I said, all of these that I'm at least mentioning right here make the assumption, even if it's not necessarily over the tropical ocean, assume kind of homogeneous surface conditions. Okay. Okay. So what I'll do first is I'm going to talk about the Amazon and some of the experiments and things like that that we've done, some examples, and then I'll move to the North American monsoon. Again, focusing on observation, some of our experiments, things like that, and pointing out relationships to what other people, for example, Adrian and Simon, have said today. Okay, so yeah, in the central, and particularly when I worked in the central Amazon for many years, I mean, I still work there remotely, so to speak. Okay, but it's basically dominated by deep precipitating convection. Okay, very, very, very continuous. There's a season that's dry, depends, but it's never more than a couple months. Okay, even then it still rains quite a bit. Okay, and kind of this is what it looks like. Lots of water, lots of vegetation, lots of mosquitoes. Okay, so basically, here's the two things that I want to focus on. The coastal Amazon region right here. Okay, it's what they call sea breeze dominant, and I'll say a little more about that. And then the central Amazon, specifically around here, around Manaus, in the central part. The topography is relatively homogeneous, and oftentimes it's referred to as a green ocean. Why? Well, because oceans are kind of smooth and homogeneous. Well, hey, the Amazon's pretty smooth. There's not a big deal of topographic differences, but there is, you know, I mean, the convection is sensitive to the small differences. Okay, so like I said, and if you look at the Amazon, like our colleagues here from Colombia, this part here, and that part of the Amazon tends to be the wettest. It's like it rains all year long. There's very, very short dry season. As you move to the edges, you tend to get much stronger dry seasons. Okay, and then specifically on the coast too, it tends to be very, very wet. Okay. Yeah, right. So let me know how I'm doing on time, you guys, because I don't have a watch. How am I doing? What's that? 12:52? Okay, I'm on the 30s, right? That's gonna, oh man, I'm already done. Sheesh. Okay. Okay. Oh, I was getting nervous. Okay. All right. So, like I said, these small differences, even if you consider the Amazon a green ocean, if that's what you want to call it, it's flat, consistent. Okay. It's not quite true. Okay. There you do get changes in the surface characteristics, and most of it's due to the river system, the Amazon River system, which is enormous. Okay, and so you have the annual flooding and retreat or withdrawal of the water, and it basically turns like the central part of the Amazon into an ocean, literally, of just fresh water. Okay. And then another idea that's really critical and is catches a lot of people's attention in the last 10, 15, 20 years is the actual nature of the forest. How does it contribute to the atmosphere, and how does that contribute to convection? Okay. And think of this in terms of, for example, the destruction of the forest at the boundary layers, at the boundary of the forest, where they're burning to produce like more cattle and things like that, or soybeans or stuff like that, or the burning, the actual where they light it on fire. You can't, it's very difficult to light, in the deep forest, you can't light it on fire, it's too wet. But at the edges, it's much easier to do. Okay. So basically one typical kind of topographic feature that they have, in Portuguese they call it igarapé, and they're kind of just like inlet rivers, okay? And they change in size radically when you have the kind of flooding season or high water season, and then they dry out here. So this would be kind of the drier season. And you can see here, I'm in the middle of using my canoe to get to work, right? You can see, look, these huge trees are in water. Okay, here they've got some kind of palm-looking things, but these huge trees are actually in water, and then the water will retreat, it'll come back, etc. Okay, now when you get to the actual dense forest, this is about 60 kilometers northwest of Manaus. These are from the LBA experiment originally. Like I said, one of the things that people are really interested in is how does the actual vegetation, the canopy, how does it contribute water vapor to the atmosphere? How is that rained out locally? And how is that transported down towards, for example, Bolivia, Argentina? And how does that affect their precipitation? So if you get rid of the Amazon forest, it may have implications way down the line, way farther away. Okay? And like I said, there's a lot of research. This is probably the biggest, sexiest theme now in terms of the Amazon. There's also the ideas of CO2, methane production, what do you call them? Organic volatile compounds. Volatile organic compounds. Okay, lots of different things. But the canopy is it's about 40 meters high or so in general. Okay, you can climb up so like I said, this one's a really crazy experiment. Okay, it's called the Atto Tower. You can see it's 325 meters. You guys want to climb that? Does it look scary? Yeah, well, look, you have to put on, like, I don't know what we call those, helmets? I mean, what do you call them? And you have to chain yourself. Okay, it takes to walk from the bottom to the top takes about 45 minutes. Okay. But anyway, so the idea here, this Atto Tower, actually I was on the original committee back in, I guess it was about 2008. It took a long time. They started, I think, building it in about 2014 or 15, I don't remember. But they have everything there. Everything in terms of chemical measurements. They have flux measures at like every 25 or 50 meters. There's another little site over here called Campina. And they have different remote sensing to like radars, LiDARs, and things like that to measure the nature of clouds. Okay, so it's really spectacular. Now they have, I guess, about 7 or 8 years of data, something like that. Okay, and so we actually got accepted at Max Planck and the INPA in Brazil. They accepted our project, and we're going to install some equipment there, hopefully, in the near future. But we went to check it out. But check out doesn't it kind of look a little bit like an ocean? It's very flat. The topography is usually on the order of 100 to 200 meters, so it's not much. If you look at the forest, they look like broccoli, right? We were arguing with our colleagues whether it was broccoli or kale or lettuce, but okay, I think it looks like broccoli. Okay, and another thing to point out, it takes a really long time to get here. You have to drive about 4 hours on a highway outside of Manaus, then you have to get in a river boat. There's kind of a wait, and that's another. I think it's about an hour or so in the boat, and then it's another 30 minutes on kind of rough road. It's in the middle of nowhere. Well, not in the middle of nowhere. It's in the middle of the Amazon rainforest. So it's, like I said, the reason why they did that also is because they wanted to avoid contaminants from Manaus. So they put it to kind of northeast of Manaus, so it's kind of virgin, pure air. Doesn't have the contamination from the urban region. Okay. All right. Also, this gives you an idea, again, of the water. This is the Watumã River. Okay. And so it's basically, it'll rise and fall too, but it just, comes up all the way to the forest. Okay. So many, in 2011 and 12, we set up a dense network, and it's what we call the dense GNS network. I'll describe more of this technique on my talk on Wednesday. Okay, but in Manaus, we set up a really dense network of these equipment to look at column water vapor, or precipitable water vapor that was mentioned earlier. Okay, we had sites that the flux tower that I showed you was this one here, like I said, about 60 kilometers. Okay, and we had some in the other kind of rural areas. But take a look. All right, it's a green ocean, it's flat, but you also do have topographic effects. You have kind of river city, so to speak, river urban, river, what we call them, it's not really like a peninsula, but there's a little open area, a little land mass here, and the river is huge. I mean, it's really wide, okay? And look at here, you have all these little like igarapés. Again, the elevation difference, very small. But when you actually look at the behavior of water vapor, column water vapor in particular, how much is in the total column, you do find differences based on your location. The wind in this region, like I said, typically comes from this way, kind of the easterlies, and the Atto Tower would be way over here somewhere. And so you actually can get like a diurnal cycle, like a sea breeze, but you would call it like maybe a river, I don't know, a river city breeze. Okay. So from here to here is about 20 kilometers. Okay. Oh, and look, because I knew that the Go Amazon was going to come, because I was also part of that committee too, I installed I installed a site there too before they came, just to have some more data. Okay. And that's where my house is actually located. Okay, so take a look at this. This will be kind of a first result, so to speak. Okay, water vapor convergence. I guess you didn't really talk about that, Adrian, but that's basically when you have water vapor being forced together, and it can rise and then fill up the column with water vapor. That could be convergence. I mean, you can think of it in other physical processes. No, so take a look. The differences are not radical, but you do see. At the rainforest site, and these are for the dry to wet season, the dry season, and the wet season, okay, you can see that the increase, the strength, so to speak, of convergence over the rainforest is much larger than any of the other regions, okay. I think probably most interesting here, if you look downwind and upwind on the local riverside, look at the downwind side, the behavior is very weak. So even that's just a little, the city's only 60, 70, 80 meters higher than the river. There's an actual local effect. And that was something that Adrian mentioned a little bit about forced lifting, but this is very small, but it still has an effect. You can see upwind, it's much stronger. The water vapor convergence. These are measured in terms of like deviations from an average. This is the diurnal cycle, and not surprisingly, the convergence is greatest in the early afternoon. Okay, so that's one example where topography makes an effect. Okay. Now, sea breezes, that's a big issue. Oh, that's kind of ugly. Okay, yeah, it didn't show up very nice, but okay, whatever. Sorry, I don't know what happened with my. Sea breeze front, take a look at all, how much coastal lineage there is everywhere across the planet. Okay, so it's actually an important phenomenon. Okay, and basically what happens is you can get heating over the surface, the land surface, and it tends to be a bit cooler over the ocean surface, and so that leads to kind of a higher density air flowing in, and that forms like maybe almost you can think of it like a little cold front or a little cold pool, okay? And that can help force water vapor convergence or moisture convergence, which can form or cause convection, okay? So how you see or what happens in these areas is going to be very different out in the middle of the ocean because you don't really have a reason to have that forced convergence just by itself due to heating. You might have it because, as Adrian was mentioning, convection itself produces a cold pool, and then it can lift air and present the next series of convection. Okay, that's what those arcs that he showed in his image. Okay, so we set up another network of our measurements with GPSs in Belém. That's along the coast, well, not right along the coast, but it's in the coastal region. And this was during the GPM Chuva experiment. So this is what was going to replace the TRIM satellites measuring precipitation. Okay. Now, what can happen in Belém, in particular, is you get these really monstrous squall lines. Okay, and I think you did mention the word, Adrian, in your talk, if I remember, from 30 minutes ago. Okay. And these are long lines of convective activity, and they can penetrate. This is a picture of Belém. One of my colleagues there, Ludmila, sends me pictures. Actually, she sent me a video last night where she filmed a lightning stroke with her handheld camera. So if anybody wants that, send me an email. Okay. But so these things form on pretty much kind of a daily basis. Okay. So here's a little from our experiment. Our experiment was only about 7 or 8 weeks long. So what we did, just kind of simply, we used, again, the GOES satellite imagery, looking at the cloud top temperature, and we just looked at convective days versus non-convective days, just kind of a simple way of assessing. So Belém is like right around here. Okay, so it's a little distance from the coast, but take a look. So here's convective days. These are non-convective days. And notice the difference. On the convective days, you'll get the formation, here they come, of these like linear kind of squall lines, and they propagate and result in convection inland. Okay. On the non-convective day, note that no line of convection forms here. Again, these are averages, so they smooth out a little bit of the things. Okay. So this interaction here, this interaction here between the surface, land surface, and the ocean has a very important role in initiating convection. Okay. Now, what's really spectacular, and you kind of saw it in one of the figures I showed at the beginning of the talk, these little, initial squall lines that form along the coast can penetrate in. Take a look how big this thing is. And it's all moving in a single line. This is like 1,000 or more kilometers long. That's pretty damn organized. You're not going to find that in the ocean. Okay? And it can propagate, and I know from experience that these things can actually arrive to Manaus, which is, like I said, I don't know, 1,000 kilometers, maybe even longer, 2,000, I forget, from Belém. Okay? They can propagate and actually go all the way to Colombia. And they live for like a little more than a day or so. Now, obviously this depends on certain types of conditions atmospherically once it passes away from the sea breeze, but the sea breeze is the initiation point of the deep convection. Okay. Okay. Now, a recent study, let's see, where's Deanna in here somewhere? Deanna? Oh, there she is. Oh, she was sleeping over there. I woke her up. Sorry. I'm sorry. What we've done is we've looked at, again, radiosondes and also our GPS data, which I'll describe next time. and we looked at convective activity. And one thing that we did here, and think about the nature of convection and its strength and intensity, we looked at it in two ways. Intensity in terms of lightning and intensity in terms of precipitation. And you might say, well, lightning, who cares? Unless you get struck by it, right? But humanity needs water, so precipitation is the most important. But the interesting thing about lightning, this is specifically the Vaisala lightning data, is that unlike precipitation, it's continuous in time and space. Okay? Precipitation is a point, especially if you measure it on the ground. How accurate can that possibly be to represent an area of 100 kilometers? That point, maybe it rained really hard and it didn't rain anywhere else. Or it didn't rain at all at that point and it flooded everywhere else. Lightning doesn't do that. Okay, lightning is continuous in time and space, so you can get an idea. So what we did was we looked at these squall lines and these just daily convection in Belém, and we came up with these categories. And it was over. Well, it's done again. My format is not very good, but it was 5 years of data. Take a look at how much it rains there. Okay. So we made these categories, convective days versus non-convective days, and then within the convective categories, we had light, that is kind of weak, moderate, strong, and extreme, okay? And then, so how does precipitation and lightning correlate? And again, it's different microphysical processes in the clouds that can lead to, that's another thing that we have to think about with convection, okay? So convective days and precipitation, okay. They match 80%, 86% of the time. That's pretty good. Okay. Non-convective, they match 70% of the time. Okay, they're cohesive. But look what happens when you start heading towards like the more extreme events. They're the same number, but they only coincide 19% of the time. So a really super heavy rainstorm, it does not happen when you have a really heavy lightning storm. Okay, can you think of why that might be? Any guesses? Who wants to earn some money? I got some money here. Okay, apparently not. What is the variable that I tend to be interested in? I've mentioned several times already. Water vapor. Okay, so let's take a look. So what we did is we said, all right, let's take a look at the vertical water vapor profile, okay, and see how they behave. Maybe that can suggest a difference, thinking of these ideas of picking parameters or critical variables to talk about convection or represent it, okay. So this is the precipitation side, and this is the lightning climatology, if that's what we want to call it. Okay, so take a look, and it makes sense. Okay, the extreme precipitation. Okay. All right. I'm sorry, I think I screwed up. Sorry. Okay. This one is the precip. Sorry. This one's the precip, and this is the lightning one. Okay, sorry, I mixed that up. Okay, so take a look here. The precipitation extreme, your specific humidity, which now you're experts in that variable, okay? The perturbations are way stronger in high precipitation days. Why does that make sense? Well, because if there's a lot more water vapor in the atmosphere, chances are you can produce a lot more precipitation, all else being equal. Okay, take a look for the extreme lightning. It's the opposite. Those tend to be dry days, well, at least in the upper atmosphere. Notice, too, that regardless, the surface doesn't change much. Now, you're going to have people that are going to talk in the near future. For example, Arturo Quintanar. Is he here? No? Okay, well, let's talk bad about Arturo. Okay. So one of the ideas, and this is actually much more important than the Amazon, it actually refers to the monsoon all over the world, is how much does the surface influence? water vapor, how much evaporation locally goes into precipitation. Okay. Here it's not real obvious. They seem to basically be the same. Okay. All right. So now we're going to move to the monsoon. Okay, so that was the Amazon. Like I said, I'll talk a little bit more about specific details and related to theory in my next talk. Okay, so here we got a nice lightning storm. One thing nice about the monsoon area, and when I say that, I'll show what I mean. That's northwestern Mexico, southwestern U.S. Okay, because it's a relatively dry climate, the base of the clouds are really high. So when you do get lightning, it can be really, really intense. Okay, this one, I took this picture when I was a little baby. Well, maybe not a little baby. I don't know, about maybe 16, 17 years old. Okay, we went out at night after work, and I drove with a friend. And this is about maybe 60, 70 kilometers north of Mexicali. You guys know where Mexicali is? So it's just an hour in car north of the border. Very dry, very, very, very dry desert region. And we sat out there, and these are cameras with, with lenses, and you put them on a tripod, and you push the button, you let it go. So he caught a similar one. I caught this one, and this is an interstate. This is California, so the most important things are highways. Okay. Okay, they don't understand that joke. All right. So anyways, but it's part of this monsoon season. Okay, so when you think of Mexico, take a look at this map. Okay, and this is based on Conagua. You're kind of, I shouldn't say you're, because there's Colombianos here too, right? The company, not the company, the government agency that deals with, for example, the meteorological service and things like that. And you can see this region up into here is what we typically refer to as the monsoon region. Okay, how am I doing on time, Simona? Oh, okay, get going. All right. So basically, the idea here, and there's some, I don't know, Simona, you'll talk a little bit about this too, or no? Okay, no, I'm pure monsoon. Okay. So basically, what the original studies said, let's take a look at the behavior of the precipitation, and it has a very similar behavior in some respects to, like, for example, what you see in India, the king of monsoons, or maybe even northern Australia, okay, or southwestern Africa, okay. So typically, what happens is, in this area down here, and from our people, Mexico City people, that about end of May, it's starting to rain. June, raining pretty hard, almost every day. Okay, and then it kind of progresses up northwest. Okay, and it tends to decrease as you go up towards the northeast, like Monterrey and those areas. So there's kind of a seesaw. Okay, and remember that here in Mexico City, like about mid-July to early August, also the precipitation decreases. Okay, sometimes what they call the canicula, here, I mean locally, and another thing is the midsummer drought, if you go farther down in Central America. Okay, so basically the idea is that this band of showers and rainy spreads up even to southern Arizona, a little bit of southeastern California, New Mexico, and sometimes it can go up even farther, no? And this usually starts up here in about early July, okay? And one of the big arguments, and actually this argument has resurged again. I don't know why. Well, I don't want to say I don't know why. I know why. But the idea is most of the moisture comes along from the Gulf of California, Eastern Pacific, and penetrates upwards. And that from the Gulf of Mexico, it can provide some of the higher level moisture that can be important for letting convective towers survive in rain. Okay, and like I said, this has become an issue again. Okay, now I took these out of my original paper back when I was a youngster, so this is actually for my master's thesis. And so put your time into your master's thesis. I checked the other day, And according to Google Scholar, this has almost 1,500 citations. That's a lot. I don't deserve it, but it's a lot. Okay. And so anyways, here's the idea. This is basically just showing that what the kind of setup, so to speak, of the monsoon circulation is associated with this kind of penetration or northward movement of a high pressure system, one of the subtropical highs, that moves up over into kind of this part of the United States, okay? And when it sets up in a stable position, that brings in these kind of easterly winds here, and the winds here start to weaken. The westerly winds tend to be really, really dry in the western part of the U.S. and Mexico. Think of like Ensenada, Ensenada, Cuauhtemoc is somewhere around here, right? There he is, okay? Baja California, Tijuana, okay? Those winds tend to be very dry, it tends to be very stable. You don't really get thunderstorms there, okay? So this moves up, and when this high pressure shifts up and down, that controls whether you get what they call bursts, that is lots of rainfall, or breaks, kind of a disminution, or what we say in English. I don't remember how to say it. Diminishing amounts of rainfall. Okay, that actually comes from India. That terminology, burst and break. Okay, so again, what's my point of this? I'm trying to show that topography and local surface conditions, landscape, and even vegetation can have a real impact on the occurrence of convection. Okay, so here we did an experiment a few years back. Okay, this is near Rayon in Sonora, if you know where that is. Okay, and you can see this is actually after it's already started to rain, because you look at the vegetation's pretty green, and then there you have a lot of these mountain valley areas there. Okay, so the by mid-September it starts to withdraw. Okay, the rainfall totals can be kind of heterogeneous, that is kind of dotty all over the place, but they tend to be most consistent over the Sierra Madre Occidental, okay? And a really large portion, particularly in the flatlands, are associated with the formation of mesoscale convective systems. And I guess Adrian is going to talk a little bit about mesoscale convective systems, or maybe? No? Okay. Okay. Here's just an example from GOES, okay? These systems, I mean, it's a little hard to tell, but here's Baja California. Okay, this would be like Mazatlan, and this would be like the border with Sinaloa and Sonora. So these monsters, again, look at how big this thing is here, organize and form. The little black dots on here, X's, those are lightning strikes, but this is just a kind of an instantaneous 15 minutes or something like that. Okay, and the really blue, it's really cold cloud top temperature, that means it's really deep convection. Okay, these things tend to propagate off into the lowlands. Okay, we did an experiment back in 2013 with University of Arizona, University of Sonora, Sinaloa, UACJ, a bunch of different Mexican universities. Okay, and what we did, which is something unusual, is we actually set up transects crossing the Sierra Madre. Okay, and then we also did along the coast too. Okay, and there were motivations for that. One of the name, which was the biggest experiment ever done in the monsoon region, one of the failures, so to speak, of they didn't cover the high elevation area, which was critical. Okay, and I actually asked Dick Johnson publicly at an AGU meeting I just said, if there were anything that you would change about the name or that you guys think you did wrong, what would it be? And he said, well, we didn't have any observations in this area. And I said, thank you, you just won the Nobel Prize. Okay, so now, is there anybody who's been in that region? Anybody from there? Been there? Okay, okay, well, yeah, okay. I don't know. You look familiar, but okay. So you're from that area?
What's that? Oh, Nayarit. Okay, yeah. Okay, I know what you're talking about. That's much farther south. Okay. Okay, but take a look how radical the elevation change is. Here's the amount of kilometers from the coast, Quino, Bahía de Quino, okay? And it's crazy. Okay, once you get over on this side, it's what they call the Mexican altiplano, or plateau, and it's flat and, I mean, hills and stuff, but it's not particularly. But so you can imagine that this configuration is going to have a very important effect on the nature and intensity and origins of convection, which it does. Okay, so, okay, speaking of dorks, okay, this is back when Arturo was only 65 years old. Okay, so here's like, this is actually Sinaloa. This is probably closer to Sinaloa, not too far from Culiacan. And so you can see, all right, here's one condition. And then when you go over to Chihuahua, this is what it looks like. Well, in one part, this is Samalayuca, so it's kind of south of Juarez a little bit. And then, of course, you have the Sierra Madre, okay, where a lot of the convection initiates. Okay, look how green it is, too. Okay, all right. So again, I stole this from our original paper. A really curious phenomenon, and this was noted way back since like the 1930s or 40s, or maybe, I forget exactly the original date. But what happens is that a lot of times you can get like a hurricane or a major storm passing by kind of the mouth of the Gulf of California, and it will cause a perturbation in the flow, and it will send a massive wave, so to speak, penetrating upward of water vapor. Okay, and then we call it a Gulf surge. Okay, and these surges can tend to lead to particularly large storms for southeastern California, southern Arizona. Okay, and they've become very famous, and they have to be predicted. If you think of your modeling, and all of a sudden you're going to have a big stream of water vapor coming up the Gulf. Okay, so from those coastal ones that I showed you, the coastal Los Mochis, that's Sinaloa, Quino, and then Puerto Peñasco, which is kind of the top end of the Gulf. Take a look. You can really follow these things. Okay, this is column water vapor, precipitable water vapor. Not much of a change in Los Mochis. Why? Well, because it's always really humid there. Okay. Then as you get up to Quino, it's a big increase. And then where the biggest increase is Puerto Peñasco, because that's really dry. Okay. Well, really relatively dry. It's desert, basically. Okay. So you see different events here. I'm saying if you're thinking of people that are actually want to predict and know, that's not a bad thing to have for your models. Okay. Also, your model should be able to replicate something like this too. Okay. So we did, and actually, Cuauhtemoc, and let's see who else. What? I got it. Okay, another 15 or 20 minutes, just like everybody else. Okay. So we set up what we call the hydromet, and this was relating to another issue, and kind of like think about the Amazon. There have been people that argue that the evaporation from the local, and I think Arturo is going to talk about this, the local fluxes, surface fluxes in the monsoon can actually contribute to deep convection, okay? And if you look at just in the Sierra Madre, they actually get quite a lot of variety in terms of the ecosystems. So it's not all the same type of vegetation, okay? And look at how radical it changes, okay? This picture, I think I took it like in May, so the rainfall hadn't started yet. And then this one was probably like mid-July, August. Look at how green it is, no? It's the same general area, okay? We were heading to Badiraguato with my buddy El Chapo, okay? I probably shouldn't say that because this is being recorded, no? Okay. Okay, yeah, here's another example. So people have been looking at this at Carlos Lizárraga from the Unison. These people have been looking at, look at how fast this is. This is southern Sonora, okay? Look at how rapid the green up is. That's pretty crazy, okay? So the question, Some argue that this evapotranspiration is an important source of water vapor, okay? All right, let's take a look. We've done a bunch of these. I'm just showing one right here just not to kill you guys off. So we worked with the guys at USDA, Russ Scott, who's been working in the monsoon stuff for many years, okay? Take a look. This is lightning, so you just know when there's convection, convective days, non-convective days, okay? Here is latent heat flux contribution of water vapor, how much is coming up from the flux, okay? And here's the change in total water vapor in the atmosphere. Okay, do you guys see much of a relationship? Look, you can see this can be negative, can be positive, and what do you say, the deviation is really large. Look at the deviation of the latent heat flux from the surface. Is that really large? Okay, and that's what we found so far at every single site we've done this for, okay? So let's see what Arturo says. I'll raise this issue. I don't know if he's making the argument that it's really important, so I shouldn't say that. Okay, I'll do this real quickly. This is from my student Omar, who recently graduated almost 2 years ago now. Okay, take a look. Goes with lightning imposed on top of it. So you can see how these, and this is related a little bit to, I think Christian is going to talk about tuts and, okay. So we'll run it through one more time real quick. Here you can see there's like a little bit of a circulation, which can also have an effect, obviously, on convection. And then you see them forming over the Sierra Madre, and then you can see they go propagando. Okay. Okay. Typically, it's in the early evening. This is from our experiment in 2017. I don't know. Do you know Ben Lintner? Okay, that's Ben, and that's another colleague from Sinaloa. Okay. So take a look. June, July, August, September. Most of the origin of the MCSs, these organized convective systems, is over the Sierra Madre, and then it goes propagating towards the Gulf of California, or the Mar de Cortés, because we have to worry about that, right? Didn't Trump say that it's going to be the Gulf of America? So I probably should be careful with that too, right? Okay. So here's just a general... my student Omar, he has a very, or ex-student, he has a very interesting way of tracking convection with using GOES imagery, okay? But anyway, so you can see basically most of the MCSs start over the Sierra Madre, okay? And take a look at the diurnal cycle, okay? This is when they begin. Yeah, it makes a lot of sense, 3, 4, 5 in the afternoon. And then this is over the Sierra Madre. And then when they arrive at the Gulf of California, or the Mar de Cortés, you can see they die around midnight or even into the early morning. Then they're gone. There's none by 6, 7, 8, 9 in the morning. Okay, so that's how they propagate. Okay, and here's just some figures showing how they propagate. Red is where they begin, blue is where they dissipate. Okay, there's some north-south too, or north-south or south-north. Okay, but very few start and go to the east, over the dry area of Chihuahua and Durango. Okay, and what we did, this part won't make a lot of sense to you, but there have been arguments, and Adrian has already mentioned it a few times, about how do these things propagate. He's mentioned cold pools, okay? There are other people like maybe Brian Mapesy types, who argue that it's gravity waves, that the convection produces gravity waves, and that perturbs the atmosphere, and that helps them propagate. So we did a simple, what's called a Hall-Mahler diagram, made averages of their propagation speed. Again, this is just very, what would the word be? I don't want to say simple, but just like a first approximation, okay? And what we found was that what's consistent is that the speeds are always about 5. That is how the storms move. It's about 5 meters, 10 meters, 5 meters, 6, 7 per second. If it were gravity waves, it would be a lot faster, okay? Don't tell Brian that I'm talking bad about him, right? Okay. So, okay. Okay, thank you. Did I make it on time? Okay. So next talk, I will go into some detail about how we actually use the column water vapor to challenge theories, other people's theories, and other types of measurements too. So are there any questions? You want to hear about the visita with El Chapo?
Dave, there are some guys from DEA waiting for your side.
From the what?
DEA.
Tell them I'm a big Trump supporter. I don't know. Okay. So anyways, we can do chisme if you want later.
Okay. Any question?
Any questions? Don't be afraid. Okay. All right. So I guess we have lunch now for an hour and a half. And I think I saw Vanessa or...
I'm going to give a message. Perhaps it's better to give it in Spanish to explain it better.
Oh, okay. Okay.